Look up at the night sky. What you see is beautiful, a tapestry of distant lights, but it's also a lie, a picture from the past. Every star, every galaxy is a historical document, its light traveling for millions or even billions of years to reach your eyes. But there's a deeper, more profound secret hidden in that darkness, a reality so strange it challenges the very foundations of our understanding. Our universe is not static. It is not simply existing. It is growing, stretching, and expanding at an accelerating rate, pushing the boundaries of the cosmos into an unfathomable, infinite future. This single, observable fact, the infinite expansion of the universe, is perhaps the greatest mystery in all of science, a puzzle that has consumed the brightest minds for a century and continues to defy easy explanation. We are living inside of this grand, dynamic entity, yet its ultimate behavior remains one of the most hotly debated and fascinating topics in modern cosmology. Imagine everything you know, every galaxy, every planet, every atom, all riding on a fabric of space-time that is relentlessly stretching, carrying us into a future we can scarcely comprehend. This isn't just an academic curiosity, it's the ultimate fate of reality itself, and it begs a question that touches on the philosophical, the spiritual, and the scientific all at once. Where is all of this headed? The answer is not simple, and it is not singular. It is a landscape of possibilities, a collection of theories ranging from the rigorously mathematical to the breathtakingly speculative. That is the journey we are embarking on today. We are going to explore 30 incredible theories about the universe's infinite expansion. We will venture from the solid ground of established physics through the strange and counterintuitive realms of dark energy and quantum foam, and out to the very edges of scientific imagination where concepts like parallel universes and cosmic rebirth are seriously considered. This voyage will challenge your perceptions of space, time, and reality, presenting ideas that are as humbling as they are mind-expanding. But don't worry, we're going to navigate these cosmic waters together, breaking down each complex concept into a fun, accessible, and utterly captivating narrative. So find a comfortable spot, open your mind, and prepare to have everything you thought you knew about the cosmos turned inside out. Let's begin. To understand where our universe is going, we must first understand where it came from, and for that, we must begin with the single most important idea in all of cosmology, the Big Bang. This isn't just a theory about a loud noise. It's the story of the origin of everything, every atom, every force, the very fabric of space and time itself. Picture this, all of the energy and matter that constitutes our vast observable universe, containing hundreds of billions of galaxies, each with hundreds of billions of stars, all compressed into an unimaginably hot, infinitely dense point, a singularity. Then, roughly 13.8 billion years ago, this point began to expand. Not an explosion into pre-existing space, but the very creation and expansion of space itself. Think of the surface of an inflating balloon, with galaxies like dots on that surface moving away from one another as the balloon stretches. That initial, unimaginably rapid stretching from a hot, dense state is the Big Bang, and it set the entire cosmic expansion in motion. But how can we be so confident about an event that occurred so long ago? The evidence is etched across the sky. In the 1920s, astronomer Edwin Hubble made a monumental discovery. By observing distant galaxies, he found that the light from them was shifted toward the red end of the light spectrum. This redshift wasn't a property of the galaxies themselves, but a consequence of their motion away from us. The farther away a galaxy was, the faster it appeared to be receding. This was the first direct observational evidence that our universe is not static, but is actively expanding. The second, and perhaps even more profound, piece of evidence came in the 1960s entirely by accident. Arno Penzias and Robert Wilson, two radio astronomers, were troubleshooting a persistent, faint hiss in their massive antenna. They pointed it in every direction, they cleaned out pigeon droppings, yet the noise remained a uniform microwave static that permeated all of space. They had accidentally discovered the cosmic microwave background radiation, the cooled-down remnant glow from the early, hot universe. This is the afterglow of the Big Bang itself, a snapshot of the cosmos when it was just 380,000 years old, cooling from an opaque plasma into a transparent gas and releasing this primordial light. This discovery was the smoking gun, transforming the Big Bang from a compelling idea into the established bedrock of modern cosmology. It provides the essential starting conditions for everything that followed, including the expansion we observe today. Without the initial impetus of the Big Bang, galaxies would not be flying apart, and we would not be having this conversation about an expanding cosmos. It is the foundational event that set the stage for every theory of cosmic fate that we will explore. But that initial expansion from the Big Bang, while colossal, wasn't the whole story. Cosmologists soon realized that the standard Big Bang model left some perplexing questions unanswered. If the universe started from a tiny, chaotic point, why does the large-scale cosmos appear so incredibly uniform? Why is the cosmic microwave background radiation coming from opposite sides of the sky, almost exactly the same temperature? This is known as the horizon problem. In the standard model, there hasn't been enough time since the beginning for light or heat to travel across the universe to even out these temperatures. It's like walking into a room where two people on opposite sides are wearing identical outfits without ever having communicated. The second puzzle is the flatness problem. Our universe's geometry appears remarkably flat, meaning parallel lines stay parallel, and the angles of a triangle add up to exactly 180 degrees. For the universe to be this flat after billions of years of expansion, its initial conditions at the Big Bang would have had to be fine-tuned to an absurdly precise degree, like balancing a pencil on its tip for eons. To solve these profound puzzles, physicist Alan Guth proposed a breathtaking addendum to the Big Bang in the 1980s, a theory called cosmic inflation. This theory posits that a tiny fraction of a second after the initial singularity, the universe underwent a brief, unimaginably violent period of exponential expansion. For a sliver of time, from about 10 to the negative 36 seconds to 10 to the negative 32 seconds, the universe didn't just expand, it inflated, doubling in size at least 90 times over faster than the speed of light. This doesn't violate Einstein's theory of relativity, which states that nothing can move through space faster than light because inflation was an expansion of space itself. This explosive growth stretched a subatomic speck of space into a region larger than our entire observable universe, smoothing out any wrinkles or temperature differences in one swift, colossal stroke. This explains the horizon problem. Everything we see was once in close contact before inflation blew it apart. It also explains the flatness problem. Just as inflating a balloon makes its surface appear flatter and flatter from any local viewpoint, cosmic inflation stretched the fabric of the universe into the geometrically flat canvas we observe today. But what could possibly power such an epic event? The leading candidate is a hypothetical field that permeated all of space, known as the inflaton field. Think of this field like a vast cosmic energy landscape. In the earliest moments, the inflaton field was trapped in a high-energy state, a sort of false vacuum, and its immense repulsive gravity, a kind of anti-gravity, drove the frantic expansion. As this field eventually decayed and rolled down to its lowest energy state, it released a tremendous burst of energy and matter, effectively reheating the universe and seeding it with the tiny quantum fluctuations that would, over billions of years, collapse under gravity to form all the galaxies, stars, and planets we see. Cosmic inflation is more than just a solution to ancient puzzles. It is the crucial bridge between the primordial singularity and the more stately Big Bang expansion that followed. It set the initial conditions for everything that came after, creating the uniform, flat, and structured universe that allowed for our own existence. After inflation settled and the universe continued its expansion under the gentle pull of gravity, cosmologists assumed they had a good grasp of the cosmic future. The prevailing belief was that while the universe was indeed expanding, the mutual gravitational attraction of all its matter would act like a cosmic brake, gradually slowing the expansion down over time. The ultimate fate hinged on a simple question: was there enough matter to eventually halt the expansion and pull everything back in a big crunch, or would gravity merely slow it to a perpetual coasting halt? This fundamental question drove one of the most ambitious observational projects in the history of science. In the late 1990s, two independent teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, set out to measure this deceleration by observing a specific kind of stellar explosion, a Type 1 supernova. These supernovae are what astronomers call standard candles, as they all explode with roughly the same intrinsic brightness. This is a cosmic gift because by measuring how bright they appear from Earth, you can accurately calculate their distance. And by analyzing the redshift of their light, you can determine how fast they were moving when they exploded. The plan was straightforward. Look at extremely distant, and therefore ancient, supernova to see how much the expansion of the universe had slowed down in the past. What they found, however, sent a shock wave through the entire field of physics. The distant, ancient supernovae were fainter than their redshifts indicated they should be. This meant they were farther away than anyone had predicted. The only possible explanation was that the expansion of the universe was not slowing down at all, it was speeding up. Some mysterious, repulsive force was overpowering the gravitational pull of all the matter in the cosmos, pushing galaxies apart at an ever-increasing rate. This discovery, which earned the teams the Nobel Prize in Physics in 2011, was completely unexpected. It was as if you threw a ball into the air, and instead of it falling back down, it shot away from you faster and faster into the sky. The universe, it seemed, had a secret engine of acceleration. This mysterious agent was given a name that reflected our profound ignorance about its true nature: dark energy. So, what could this dark energy be? The leading and simplest candidate takes us back nearly a century to an idea proposed and then famously discarded by Albert Einstein himself. When Einstein was developing his theory of general relativity, his equations described a universe that was either expanding or contracting. But the scientific consensus at the time, including Einstein's own belief, was that the universe was static and eternal. To force his equations to describe a static universe, he introduced a fudge factor, a term he called the cosmological constant, represented by the Greek letter lambda. This constant represented a kind of energy inherent to the fabric of empty space itself, a repulsive force that would counterbalance the attractive force of gravity on cosmic scales, preventing the universe from collapsing in on itself. Later, when Edwin Hubble's observations confirmed the universe was indeed expanding, Einstein reportedly called the cosmological constant his greatest blunder, and it was largely abandoned for decades. But the discovery of the accelerating universe in the late 90s brought Einstein's blunder back from the dead with a vengeance. If the cosmological constant is real, then empty space is not nothing. According to quantum physics, the vacuum of space is a seething, bubbling foam of virtual particles constantly popping in and out of existence. This vacuum energy exerts a negative pressure, a kind of tension that, according to general relativity, generates a repulsive gravitational effect. If this energy density is constant over time, as the cosmological constant suggests, then it provides a perfect explanation for dark energy. As the universe expands and more space is created, the total amount of this repulsive vacuum energy increases, driving the acceleration faster and faster. The implications of this are staggering. Current measurements suggest that dark energy in this cosmological constant form makes up about 68% of the total energy density of the universe. It is the dominant component of the cosmos, with dark matter making up about 27% and all the normal matter, every star, planet, and person comprising a mere 5%. Dark energy is now the primary architect of our cosmic destiny, shaping a future where the expansion not only continues forever but does so at an ever-quickening pace. While the idea of a repulsive force in empty space is profound, it leads us to a theory about the very beginning of everything that is even more staggering, a concept that suggests our entire cosmic history is just a tiny chapter in a much grander, potentially infinite story. Let's turn our attention to a breathtaking extension of cosmic inflation known as eternal inflation and the multiverse. We left inflation as a brief, explosive event that smoothed and flattened our observable universe before ending. But what if that shutdown wasn't universal? What if, in the grand scheme of things, inflation never truly stopped? This is the core of eternal inflation. Imagine the energy field that drove inflation, the inflaton field, as a vast, rolling hillside. Our universe represents a single valley where the field finally settled to its lowest, most stable state, releasing its energy to create the particles and forces we know. According to eternal inflation, however, most of the hillside is still steep. In these steep regions, the inflaton field remains stuck in its high energy state, and here, the repulsive gravity of inflation continues to run wild, stretching space at an exponential, frantic rate forever. Now picture this eternal, inflating background as a boiling pot of water. Every so often, in a random spot, a quantum fluctuation causes a tiny patch of that high-energy field to tunnel or roll down into a stable valley. When that happens, inflation ends in that little patch and a new, bubble universe is born, much like a bubble forming in the boiling water. Our entire observable cosmos, with its hundreds of billions of galaxies, is just one such bubble in an infinite, ever-expanding frothing sea of inflating spacetime. In this eternal picture, the process is ceaseless. While our bubble stopped inflating eons ago, the overarching meta-universe continues to inflate exponentially, constantly spawning new bubble universes in an endless, self-replicating cosmic foam. The implications of this are nothing short of earth-shattering. Each of these bubble universes forms in its own unique valley, with its own LOCL, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter. And the shape of that energy landscape determines the fundamental laws of physics within that bubble. In one bubble, the strength of gravity might be 1,000 times stronger, causing stars to burn out in mere millions of years. In another, the nuclear forces might be too weak for atoms to ever form, leaving a universe of scattered subatomic particles. Some bubbles might have 10 spatial dimensions instead of our 3, while others might collapse back in on themselves instantly. Our universe seems finely tuned for life. If the strength of the fundamental forces were different by even a tiny fraction, stars wouldn't shine, carbon wouldn't form, and we wouldn't be here to ponder it. The multiverse theory offers a powerful, if humbling, explanation for this apparent fine-tuning. In an infinite multiverse where every possible set of physical laws is realized in some bubble, it's no surprise that we find ourselves in one of the rare, hospitable bubbles where life can arise. We are not a special, central universe. We are simply a fortunate one, living in a cosmic neighborhood where the local rules allow for our existence. This transforms the question of why are the laws of physics just right, from a profound mystery into a simple statistical observation, a cosmic version of the anthropic principle. While this idea is currently untestable and resides at the frontier of theoretical physics, it represents a compelling and majestic vision of reality, one where the infinite expansion we see around us is merely a local echo of a much vaster, eternal, and creatively fecund process. While the idea of an eternally inflating multiverse presents one vision of cosmic infinity, another equally profound theory suggests that our universe's story is not one of endless, one-way expansion into cold isolation, but rather a grand, repeating cycle of birth, death, and rebirth. This is the core of the cyclic model. Imagine a cosmos with a heartbeat, a rhythmic pulse where a period of expansion is inevitably followed by a contraction, culminating in a tremendous collision or a big crunch, which then provides the seed for the next big bang, starting the cycle all over again. This idea appeals to a deep-seated human intuition about natural cycles, the rising and setting of the sun, the changing of the seasons, the very rhythm of life and death on our planet. Could the entire universe operate on a similar, albeit vastly grander, timescale? One of the most elegant and mathematically sophisticated versions of this idea comes from the renowned physicist Sir Roger Penrose, and it's known as conformal cyclic cosmology. Penrose's theory begins by confronting the ultimate fate of our accelerating universe. In a cosmos dominated by dark energy, most matter will eventually decay or be ripped apart, and black holes will slowly evaporate over unimaginable eons due to Hawking radiation. What remains is a universe that has expanded so much that it becomes virtually empty, filled only with low-energy photons and gravitons wandering through an immense, cold and dark void. In this state, the concept of scale loses all meaning. There are no rulers to measure distance and no clocks to tick off time, because all particles have lost their mass and all structure has been erased. Penrose uses a mathematical concept called conformal geometry to show that this vast, empty, cold end state of the universe is physically identical to the hot, dense, small beginning of a new one. In this framework, the Big Bang wasn't a unique, singular beginning of time, but rather the transition point from a previous cosmic cycle, which Penrose calls an aeon. Our universe is simply the current eon in an endless chain. The beauty of this model is how it elegantly sidesteps the problematic singularity that plagues the standard Big Bang theory. A singularity where density and temperature become infinite and our laws of physics break down, marks the beginning and end in traditional cyclic models. But in conformal cyclic cosmology, the universe never reaches an infinitely dense point. Instead, as it expands toward infinity and loses all scale, it smoothly and mathematically resets, becoming the low-energy, high-symmetry starting condition for the next eon. One of the most tantalizing pieces of evidence Penrose and his colleagues have pointed to are strange, circular patterns of uneven temperature in the cosmic microwave background, which they call Hawking points. These, they propose, could be the imprints of supermassive black holes from the previous eon, their final evaporation emitting colossal bursts of energy that were imprinted onto the fabric of our own universe's birth. While this interpretation is highly controversial and not widely accepted in the cosmology community, it demonstrates the theory's potential to make testable predictions. The vision this theory offers is simultaneously humbling and comforting. It suggests that the fiery death of one cosmos is not an end, but a transformation, a prelude to a fresh start. It offers a form of cosmic immortality, where the information and energy of our universe are endlessly recycled into new forms, new laws, and new possibilities across an infinite succession of eons. Moving from the vast cyclic view of the cosmos, we encounter a theory that challenges the very nature of reality itself, suggesting that the universe we perceive is a magnificent and convincing illusion. This is the holographic principle, a radical idea proposing that our seemingly solid, three-dimensional reality, with its stars, planets, and people, might actually be a projection, a hologram encoded on a distant two-dimensional surface. The origins of this mind-bending concept come from an unexpected place, the study of black holes and the fundamental nature of information. In the 1970s, physicist Jacob Bekenstein made a startling proposition. He argued that a black hole's entropy, which is a measure of the disorder or information content within a system, is proportional to the surface area of its event horizon, the point of no return, and not to the volume of the black hole itself. This was counterintuitive. In our everyday world, the amount of information you can store in a box depends on its three-dimensional volume. But for the most extreme objects in the universe, information seems to be painted onto their two-dimensional boundary. Stephen Hawking soon confirmed that black holes aren't completely black. They radiate energy and slowly evaporate due to quantum effects, a process now known as Hawking radiation. This raised a terrifying paradox. If you throw an encyclopedia into a black hole, it vanishes behind the event horizon. The black hole eventually evaporates, releasing Hawking radiation. But this radiation appears to be completely random and featureless, containing no information about the encyclopedia whatsoever. This would mean the information is permanently lost from the universe, violating a core tenet of quantum mechanics which states that information must be preserved. The resolution proposed by physicists like Gerard T. Hooft and Leonard Susskind is that the information isn't lost at all. It never actually falls into the black hole in the three-dimensional sense. Instead, it is perfectly encoded and stored on the event horizon's two-dimensional surface, like a cosmic DVD. When the black hole evaporates, that information is faithfully imprinted onto the outgoing Hawking radiation. The three-dimensional interior of the black hole, with all its apparent depth, is a projection of that two-dimensional data. This idea was then taken to its ultimate cosmic conclusion. If a region of space can have its entire physical content described by information on its boundary, could the same be true for the entire universe? The holographic principle boldly asserts that yes, our entire observable universe, with its hundreds of billions of galaxies, is a vast holographic projection. The screen for this cosmic movie is the boundary of the observable universe, an immense sphere at the farthest reaches where light has had time to reach us since the Big Bang. All the events, particles, and forces we experience in three dimensions are a translation of quantum bits of information stored on this remote, two-dimensional surface. This principle finds a natural home in string theory, a framework that attempts to unify gravity with quantum mechanics. In certain models, a gravitational theory in a volume of space is mathematically equivalent to a quantum field theory without gravity operating on its boundary. This is a duality, meaning both descriptions are different perspectives of the same underlying reality. So, what does this have to do with the universe's expansion? The accelerating expansion of space creates new volume, and according to the holographic view, this new volume must correspond to new information being encoded on the boundary. The growth of the universe could be understood as the increasing complexity of this cosmic data storage system. There's a fundamental limit, much like the maximum data density of a hard drive, and the evolution of the cosmos might be governed by how information is written and processed on this ultimate screen. The implications for the nature of reality are staggering. It suggests that the world of solid objects and vast distances is an emergent property, a derivative reality that arises from a more fundamental, information-based layer. Your experience of reading this, the feeling of the ground beneath your feet, the vast distances between stars, all of it could be a phenomenally detailed computation happening on a distant cosmological surface. This principle also offers a profound insight into one of physics' greatest challenges, uniting Einstein's general relativity with quantum mechanics. Gravity, in this view, is not a fundamental force like the others. It emerges from the quantum entanglement of the information bits on the boundary, much like the three-dimensional image emerges from a two-dimensional holographic plate. The holographic principle transforms our universe from a container of things into a dynamic network of information, where expansion is not just the stretching of space, but the ongoing rendering of a cosmic reality from its most basic code. So far, most of our theories have accepted the existence of dark matter and dark energy as the dominant forces shaping our universe. But what if we've been looking at the problem backward? What if the mysterious phenomena we attribute to vast oceans of invisible matter and a repulsive force in the vacuum are, in fact, telling us something much more fundamental? That our understanding of gravity itself, a force we thought we had mapped out centuries ago, is fundamentally flawed on the grandest scales. This is the radical proposition of a theory known as modified Newtonian dynamics, or MN. Instead of filling the cosmos with unseen particles, MN suggests we simply need to rewrite the rules of gravity, particularly where its pull becomes exceptionally weak. The story of MN begins not with the expansion of the universe, but with the way individual galaxies spin. In the 1970s, astronomer Vera Rubin was studying the rotation curves of spiral galaxies. According to Newton's laws, stars on the outer edges of a galaxy, far from the central bulge of mass, should orbit much more slowly than those near the center, just as Pluto orbits the Sun more slowly than Mercury. But Rubin's observations revealed something astonishing. The stars at the distant edges of galaxies were orbiting just as fast as those near the middle. The only way to explain this within Newtonian physics was to assume that galaxies were surrounded by enormous, invisible halos of matter halos that provided the extra gravitational glue to keep these fast-moving stars from flying off into intergalactic space. This was the primary evidence for what we now call dark matter. But in the early 1980s, physicist Mordechai Milgrom proposed a daring alternative. What if Newton's second law of motion, F equals ma, subtly changes when acceleration becomes incredibly small? In the faint gravitational fields at the outskirts of galaxies, where acceleration dips below a critical, tiny threshold, Milgrom suggested that gravity effectively becomes stronger than Newton or Einstein would predict. This simple modification, this tweak to the laws of physics, perfectly reproduces the flat rotation curves of galaxies without needing a single particle of dark matter. The gravity we feel in this view is all there is. It just behaves differently in the realm of the super slow and super faint. The appeal of MUND is its stunning success at the scale it was designed for. It predicts galactic rotation with remarkable accuracy, often outperforming simple dark matter models. It explains other puzzling observations, like why the observed acceleration in a galaxy always seems to correlate with the amount of visible matter in a very specific way, a relationship known as the radial acceleration relation. For its proponents, this is a beautiful, elegant solution that does away with the need to invent an entirely new, invisible form of matter that has, despite decades of searching, never been directly detected. However, MUND faces its own monumental challenges, especially when we zoom out from individual galaxies to the cosmos at large. The theory was crafted to solve a galactic problem, and it struggles to explain the behavior of the universe as a whole. The intricate patterns seen in the cosmic microwave background, the afterglow of the Big Bang, provide a snapshot of the early universe. The precise sizes of the hot and cold spots in this radiation are a powerful piece of evidence for the existence of a substantial amount of dark matter in the cosmos's infancy, which helped pull matter together to form the large-scale structures we see today. Standard MUND, in its original form, has a very difficult time accounting for these observations without some additional, unseen component. Furthermore, the theory was built to explain motion within galaxies, but it said nothing about the accelerating expansion of the universe driven by dark energy. This forced proponents of modified gravity to expand the theory, leading to sophisticated relativistic versions like tensor vector scalar gravity, or TVS. These theories are complex endeavors to build a complete description of gravity that incorporates Milgrom's ideas and works on cosmological scales. Some of these extended models attempt a truly grand unification, suggesting that the same modification that explains galaxy rotations without dark matter could also be responsible for the cosmic acceleration we attribute to dark energy. In this picture, the universe's expansion isn't being pushed by a mysterious vacuum energy, but is instead a consequence of gravity itself behaving differently over vast cosmic distances. This creates a compelling, if highly controversial, narrative that both of the great cosmic mysteries of our time, dark matter and dark energy, are not substances at all, but illusions stemming from our incomplete understanding of the most familiar force in the universe. The battle between these paradigms is one of the most fascinating in modern cosmology. Is the universe mostly made of stuff we cannot see, or are we still just learning how gravity truly works? The answer will reshape our entire conception of reality. This idea of a cyclical cosmos finds one of its most compelling expressions in a theory that completely reimagines the moment of creation itself, replacing the daunting, physics-breaking singularity of the Big Bang with a graceful cosmic rebound. Welcome to the concept of the Big Bounce and the fascinating world of quantum cosmology. The standard Big Bang model presents us with a profound puzzle. It tells us the universe began as an infinitely hot, infinitely dense point where the known laws of physics simply ceased to apply. This singularity is more than just a mathematical inconvenience. It's a glaring signpost that our best theories are incomplete, unable to describe the very origin of the reality they otherwise map so well. But what if there was no true beginning? What if our expanding universe was not born from nothing, but rather sprang forth from the collapse of a previous cosmic era? This is the essence of the Big Bounce. Picture the universe not as a one-time firework, but as a cosmic lung breathing in and out over trillions of years. A phase of contraction where all matter and energy are pulled together by gravity in a big crunch is followed not by an end but by a turnaround, a bounce, where quantum effects become so powerful that they reverse the collapse and trigger a new period of expansion, a new Big Bang. This elegant idea naturally creates an oscillating universe, a timeless cycle of death and rebirth. But for this to be more than just philosophical poetry, we need a mechanism. What could possibly overcome the colossal gravitational pull of an entire universe collapsing in on itself? The answer lies in the one realm of physics designed to handle the extremes of the very small and the very dense, quantum gravity. While a complete theory of quantum gravity remains the holy grail of modern physics, several promising approaches offer a glimpse into how a bounce could occur. One of the most developed frameworks is known as loop quantum cosmology, or LQC, which is derived from the broader theory of loop quantum gravity. In Einstein's general relativity, the universe's density increases without limit as we rewind time toward the Big Bang, leading to that problematic singularity. But loop quantum cosmology introduces a fundamental granularity to spacetime itself. It suggests that space is not a smooth, continuous fabric, but is woven from tiny, indivisible loops, a fabric of finite, discrete threads. This has a breathtaking consequence. As we look back in time and the universe compresses, this quantum nature of space acts as a sort of cosmic repulsive force. When the density of matter and energy reaches a critical, immense threshold, not infinity, but a value dictated by quantum theory, this repulsion kicks in, overpowering the attractive force of gravity. Think of it like compressing a spring. You can push it down, but at a certain point, it resists with tremendous force and pushes back. In the Big Bounce scenario, the collapsing universe reaches its maximum compression and then bounces back outward, initiating the expansion phase we are currently experiencing. In this view, the Big Bang was not the absolute beginning of time, but rather the moment of rebound from a prior contracting phase. The expansion we observe all around us, with galaxies rushing away from each other, is simply one half of an eternal, oscillating cycle. This framework elegantly removes the need for a singularity, replacing a point of infinite density with a quantum bridge to a previous cosmic epoch. So what might have come before our universe? The possibilities are as vast as they are mind-bending. The previous cycle could have been a universe very similar to our own, filled with galaxies, stars, and perhaps even life, all of which was eventually drawn together in a great contraction. Alternatively, the physical laws and constants in that prior era might have been completely different, reset during the bounce in a process of cosmic metamorphosis. Some models suggest that the bounce would smooth and homogenize the universe, explaining the remarkable uniformity we see in the cosmic microwave background without needing a separate period of inflation. Others propose that certain quantum information could be transferred across the bounce, meaning faint echoes of a previous cosmos might still be imprinted in our own. The concept of a bouncing universe profoundly recontextualizes our place in the cosmos. Our entire 13.8 billion year history, from the first glimmers of light to the formation of galaxies and the evolution of life, is just one chapter in a story that has been repeating for perhaps an infinite number of cycles, each with its own unique narrative, each ending in a collapse that seeds a new beginning. This vision offers a powerful alternative to both the one-time creation of the standard Big Bang and the eternal, accelerated emptiness predicted by a dark energy-dominated future. It suggests that the cosmos is inherently resilient, perpetually renewing itself in a grand, rhythmic dance governed by the subtle yet powerful laws of the quantum world. Now, we take a step back from the frontiers of quantum gravity and bouncing universes to revisit an idea that, for a time, was the Big Bang's greatest rival, a vision of a cosmos without beginning or end, eternally unchanging in its grand appearance. This is the steady-state theory. While the notion of the Big Bang is so ingrained in our culture it can feel like an obvious truth, for much of the 20th century it was locked in a fierce battle with this elegant, but ultimately dethroned cosmological model. The steady-state theory was formulated in the late 1940s by three formidable scientists, Hermann Bondi, Thomas Gold, and the brilliant astronomer Fred Hoyle. It was Hoyle, in fact, who famously coined the term Big Bang during a radio broadcast, intending it as a somewhat dismissive label for a theory he found philosophically unsatisfying. What these scientists proposed was a universe that had always existed and would always exist, looking roughly the same not only from every point in space, but at every moment in time. They called this the perfect cosmological principle. The standard cosmological principle, which the Big Bang also adheres to, states that the universe is homogeneous and isotropic when viewed on a large enough scale, meaning it looks the same in every direction and no place is special. But the steady-state theory went a crucial step further. It asserted that the universe also looks the same at every epoch. There was no hotter, denser past. There was no moment of creation. The cosmos was simply always there. This created an immediate and obvious problem. Edwin Hubble had already shown the universe was expanding, with galaxies moving apart. If space is stretching and galaxies are flying away from each other, the overall density of matter in the universe would naturally decrease over time, making the past fundamentally different from the present. This would violate the perfect cosmological principle. To solve this, the steady-state theorists introduced a truly radical concept, the continuous creation of matter. They proposed that new matter, hydrogen atoms, is spontaneously and slowly created out of nothingness, popping into existence throughout the vacuum of space to fill the gaps left by the expansion. The rate required was almost imperceptibly small, something like 1 atom per cubic meter every few billion years, far too slow to ever be detected in a laboratory. This tiny, constant trickle of new substance would be just enough to maintain a constant average density throughout an eternally expanding cosmos. As old galaxies drifted beyond our observational horizon, new galaxies would form from this newly created matter, ensuring the overall large-scale appearance of the universe never changed. It was a profoundly beautiful and comforting idea, a universe with no beginning and no end, requiring no singular moment of creation, and avoiding the thorny philosophical questions of what, if anything, came before. For a time, it was a perfectly valid competing model. The debate between the Big Bang and steady-state theories raged for over a decade, a true battle for the soul of cosmology. The key to resolving it lay in looking back in time. If the Big Bang was correct, the universe in the distant past should have been much hotter and denser. The steady-state model predicted no such change. The discovery that definitively tipped the scales was the one we discussed earlier, the cosmic microwave background radiation. This faint, uniform glow filling all of space is the cooled remnant of the incredibly hot, dense early universe. Its existence was a direct prediction of the Big Bang model, and its discovery in 1965 by Penzias and Wilson was a catastrophic blow to the classic steady-state theory. The steady-state model could not naturally explain this pervasive, cool background radiation. There was no mechanism within its framework for a universe that was once a hot plasma. While proponents tried to develop alternative explanations, such as suggesting the radiation was scattered starlight from ancient stars, these arguments were ad hoc and unconvincing compared to the elegant and direct explanation provided by the hot Big Bang. The CMB was a snapshot of a past that was fundamentally different from the present, directly violating the perfect cosmological principle. The universe, it turned out, did have a history. It had evolved from a hot, dense state. Despite this definitive evidence, the spirit of the steady-state theory has not completely vanished. Some cosmologists, uncomfortable with the idea of a definitive beginning or intrigued by the concept of continuous creation, have developed modern variations. One such idea is the quasi-steady-state model or the plasma cosmology model, which attempts to incorporate new matter creation and cyclical processes on a very long timescale while still trying to account for the cosmic microwave background. These models, however, are considered fringe by the vast majority of the scientific community, as they struggle to explain the full suite of cosmological data as elegantly as the now standard lambda cold dark matter model, which incorporates the Big Bang, inflation, dark matter, and dark energy. The story of the steady-state theory serves as a powerful reminder of how science self-corrects. It was a brilliant, imaginative, and philosophically attractive idea, but in the end, the evidence from the cosmos itself pointed toward a more dynamic, evolving, and ultimately more dramatic history, one that began with a bang. Now, if the idea of a universe rebounding from a previous state stretches your imagination, prepare for a concept that unfolds across dimensions beyond our own. From the realm of string theory comes an even more radical vision of cosmic origins, one where our entire three-dimensional universe is just a single slice of a much grander, higher-dimensional reality. This is the world of brain cosmology and its most dramatic story, the ekpyrotic universe. To even begin to grasp this, we need to shift our entire perspective on what the universe is. We are intimately familiar with three dimensions of space: length, width, and height, and one of time. But for decades, string theorists have proposed that for their mathematical equations to work, the universe must actually have more spatial dimensions, often 10 or 11 in total. The reason we don't perceive these extra dimensions, the theory suggests, is because they are incredibly tiny, curled up on a scale far smaller than an atom. Think of a garden hose. From a distance, it looks like a simple one-dimensional line. But if you get very close, you see it has a second dimension, a circular cross-section. Brain cosmology takes this a step further. It proposes that what we call our universe, all the particles and forces we know, with the notable exception of gravity, are actually confined to a three-dimensional membrane, or brane for short, floating within a higher dimensional bulk space. In this picture, we are like characters living on the surface of an immense, multidimensional soap bubble, utterly unaware of the greater volume in which our bubble resides. This leads us directly to the ekpyrotic model, a name derived from the Greek word for conflagration or fire. In this stunning scenario, the Big Bang was not the birth of space and time from a singularity, but a violent, transformative event caused by a collision between our three-dimensional brain and another parallel brain in the higher dimensional bulk. Imagine two enormous, perfectly flat sheets of paper representing two brains floating parallel to each other in a higher dimensional space. They are attracted to one another by a force, perhaps akin to a spring, and they are on a collision course. As they move closer and closer, the energy in the space between them builds up. When they finally collide and bounce apart, that colossal energy of impact is released directly onto our brain. This tremendous infusion of energy is what we perceive as the hot, dense state of the Big Bang. All the matter and radiation that would eventually coalesce into galaxies and stars was created in that fiery collision. This model offers a breathtakingly elegant alternative to cosmic inflation. The ekpyrotic phase, the period leading up to the collision, involves the two brains slowly moving together. As they approach, any wrinkles or irregularities on their surfaces are stretched and smoothed out, just as the wrinkles on a tablecloth are smoothed when you pull it taut. This naturally explains the horizon and flatness problems that inflation was designed to solve, but without requiring a period of faster-than-light expansion. Our universe appears uniform and flat because the colliding brains were nearly perfectly flat and parallel. But the story doesn't have to end there. This setup lends itself beautifully to a cyclic model of the cosmos. After the collision, the two brains bounce apart and our universe expands and cools, much as in the standard model. But the force that attracted them in the first place remains. Over trillions of years, as the expansion of our brain slows and dark energy potentially weakens, the attractive force will once again pull the brains together. They will collide again, igniting a new Big Bang and starting the cycle anew. In this view, the cosmos is engaged in an eternal, rhythmic dance of collision, separation, and renewed collision. Brain cosmology also provides fascinating new ways to think about the fundamental forces of nature. Why is gravity so incredibly weak compared to the other forces? A magnet can easily lift a paperclip, defying the gravitational pull of the entire Earth. In the brain world picture, the answer might be that while all other particles and forces are stuck to our brain like ink on a page, gravity, in the form of gravitons, is unique. It can leak off our brain and propagate through the higher dimensional bulk. This dilution of gravitational force across extra dimensions could explain its apparent feebleness in our three-dimensional world. Furthermore, this framework offers novel explanations for the universe's accelerating expansion. Instead of a cosmological constant or quintessence, the acceleration could be driven by a force related to the brains themselves. Perhaps the brains are not static but dynamic, and their inherent tension or their interaction through the bulk is causing our cosmic slice of reality to expand at an accelerating rate. Some models even suggest that what we call dark energy is a manifestation of a second brain floating very close to our own, its presence exerting a gentle, repulsive force on our universe. The elegance of brain cosmology lies in its potential to unify some of the deepest puzzles in physics: the origin of the universe, the nature of the forces, and the cause of cosmic acceleration into a single, coherent, though higher dimensional picture. It transforms the Big Bang from a mysterious beginning of everything into a localized event on a membrane, one of perhaps countless others in a truly vast multiverse of brains. Now we arrive at a theory so radical that it challenges one of the most sacred tenets of modern physics, a constant so fundamental it's woven into the very fabric of spacetime itself. This is the idea that the speed of light might not be so constant after all. What if, in the searing heat of the infant universe, light traveled not at 299,792,458 meters per second, but far, far faster? This is the provocative proposal of variable speed of light, or VSL, theories. At first glance, this seems to fly in the face of a century of established science. Albert Einstein's theory of special relativity is built upon the bedrock principle that the speed of light in a vacuum, denoted by the letter c, is the ultimate cosmic speed limit, a universal constant that is the same for all observers regardless of their own motion. This constancy is not just a detail, it's the glue that holds together our understanding of space and time, leading to mind-bending consequences like time dilation and length contraction. To suggest that c could change is to risk unraveling the entire theoretical tapestry. So why would anyone propose such a thing? The motivation comes from the same cosmic puzzles that drove the development of inflation. Remember the horizon problem. How can regions of the universe on opposite sides of the sky have the same temperature if they were never in causal contact? And the flatness problem. Why is the geometry of our universe so perfectly balanced? Cosmic inflation solved these by proposing a period of ultra-fast expansion. But Joe Megiddo, a physicist at Imperial College London, and others asked a daring question. What if you could achieve the same results not by stretching space itself fantastically quickly, but by allowing light and other forms of information to travel much faster in the past? Imagine two towns on opposite sides of a wide, slowly expanding plain. If the only way to communicate is by sending messengers on foot, the towns could never coordinate or share heat, and they would develop independently. This is the horizon problem in the standard Big Bang model. Inflation's solution is to suddenly shrink the plane to the size of a postage stamp, let the towns exchange messengers, and then violently inflate the plane back to its original size. The VSL approach is different. It says the plane was always large, but in the past, the messengers could run at nearly infinite speed. They could zip back and forth across the vast distance, effortlessly equalizing the temperature between the two towns before their speed suddenly dropped to its modern, slower value. In this scenario, a faster speed of light in the first moments after the Big Bang would have allowed the entire observable universe to be in thermal contact, smoothly ironing out any temperature differences and solving the horizon problem with elegant simplicity. As for the flatness problem, a variable speed of light can also explain why our universe appears so perfectly balanced. The critical density that determines whether the cosmos is open, closed, or flat depends directly on the speed of light and the rate of expansion. If the speed of light was much higher in the past, it could have driven the universe toward that precise state of flatness we observe today, again without the need for a separate inflationary epoch. The implications of this idea, if true, are nothing short of revolutionary. Our entire conception of causality, the principle that cause must precede effect, is protected by the finite, constant speed of light. If light could travel faster in the past, the cosmic chain of cause and effect could have been profoundly different, potentially allowing for connections and processes that are impossible in our current cosmic epoch. It would force a dramatic revision of general relativity, requiring a new, more flexible framework where the constants of nature are not so constant after all. Megiddo and his colleagues have worked to develop such frameworks, constructing self-consistent theories where the speed of light could vary while preserving the core successes of relativity in the later universe. Of course, VSL remains a highly controversial and speculative idea, firmly on the fringes of cosmology. It lacks the widespread acceptance and the detailed, testable predictions that inflation has accumulated over decades. Crucially, no definitive observational evidence has been found to prove that the speed of light has changed. Measurements of the fine structure constant, which depends on c, have shown no variation over billions of years. Yet, it endures as a powerful testament to scientific creativity, a bold challenge to orthodoxy that reminds us that even our most cherished constants might have a history, and that the laws of physics as we know them could be merely the settled, mature version of a much wilder and more dynamic set of rules in the primordial cosmos. But what if dark energy is not a simple, static feature of empty space? What if it's something that can change, evolve, and even intensify over time? This brings us to our next theory, a compelling alternative to the cosmological constant known as quintessence. Named after the fifth element of ancient philosophy, the substance thought to fill the heavenly realms beyond Earth, quintessence proposes that dark energy is not a constant vacuum energy, but a dynamic cosmic field that permeates all of space. Imagine the inflattened field that drove the early universe's rapid expansion, but acting over a much longer, more gradual timescale. Quintessence is theorized to be a type of scalar field, meaning it has a value at every point in space but no direction, much like a temperature map. The key difference from the cosmological constant is that this field can evolve. Its energy density can change over the history of the cosmos, meaning the strength of its repulsive push can either weaken or grow stronger as time goes by. In some models, the field was largely dormant in the early universe, allowing matter to clump together and form galaxies, only to become dominant more recently, which aligns with our observations that the acceleration began a few billion years ago. This dynamic nature opens up a spectrum of possible futures for our cosmos that are far more dramatic than the lonely, cold fate of a cosmological constant universe. One particularly startling possibility is a scenario known as the Big Rip. If the quintessence field is of a certain type, its energy density could increase over time. As the universe expands and the field grows stronger, its repulsive gravity would become ever more dominant. First, it would tear apart the cosmic web of galaxy clusters. Then, the gravitational bonds holding individual galaxies together would be overcome, sending stars flying off into the expanding darkness. As the acceleration intensifies further, even individual solar systems would be ripped apart. In the final, terrifying moments before a hypothetical Big Rip, the gravitational pull of individual stars would fail, and planets would be separated from their suns. Then, stars and planets themselves would be shredded, followed by molecules, atoms, and finally, the very fabric of space-time. The universe would end not with a crunch or a freeze, but with a violent, fundamental disintegration of all structure. While this sounds like science fiction, it is a mathematically consistent outcome for certain forms of quintessence where the field's pressure is negative enough and becomes more extreme over time. Of course, not all quintessence models lead to such an apocalyptic end. Other versions propose that the field is gradually weakening, potentially leading to a future where the acceleration slows and gravity might one day reassert itself. The true nature of quintessence is a question for observation. Astronomers are actively searching for signs that dark energy is changing by measuring the expansion rate of the universe at different points in its history with ever greater precision. Projects like the Dark Energy Survey and the upcoming Euclid Space Telescope are meticulously mapping the distribution of galaxies and the behavior of distant supernovae, looking for any subtle drift in the equation that describes dark energy's behavior. So far, the data is consistent with a simple cosmological constant, but the door is firmly open for a dynamic field like quintessence. Discovering that dark energy is not constant would be one of the most profound revelations in the history of science, forcing us to rewrite our understanding of the fundamental forces and the ultimate fate of everything we see. Yet, with so many potential fates and fundamental constants, a deeply philosophical question emerges. Why does our universe seem so perfectly tailored for life? The strength of gravity, the charge of an electron, the rate of cosmic expansion. If any of these values were altered by even a tiny fraction, stars would not form, complex atoms would never exist, and life as we know it would be impossible. This apparent cosmic fine-tuning has led some physicists to propose a powerful, if humbling, explanation known as the anthropic principle. In its simplest form, the principle suggests that we observe the universe to have the properties it does because if it were any different, we would not be here to observe it. It's a statement that seems almost tautological, but when placed within the context of a vast multiverse, it transforms from a philosophical curiosity into a potentially powerful scientific tool for understanding our place in the cosmos. Imagine a cosmic lottery with an almost infinite number of tickets, each representing a universe with a unique set of physical laws and constants. The vast majority of these tickets are losers' universes that collapse instantly, or where no atoms form, or where forces are so weak that nothing ever coalesces. But by the sheer, staggering power of infinite probability, a few tickets will, by pure chance, have just the right numbers to allow for galaxies, stars, planets, and eventually conscious observers. We, quite simply, are the living proof that we hold one of those winning tickets. This idea finds a natural home in the landscapes of eternal inflation and string theory. In the eternal inflating meta-universe, every single bubble universe can have its own unique, low-energy physics determined by how its local inflaton field settled. This creates a sprawling cosmic landscape of possibilities, a multiverse where every conceivable set of physical laws is realized somewhere. In this context, the puzzling value of dark energy, that mysterious force driving the acceleration, becomes less mysterious. What if, in most universes, the cosmological constant is vastly larger? In those realities, the repulsive force would be so powerful that it would tear apart matter before it could even begin to clump into galaxies. A universe with too much dark energy would be a thin, rapidly dispersing gas, forever empty and dark. Conversely, if dark energy were significantly weaker or negative, gravity would have quickly pulled the universe back into a catastrophic big crunch long before life could evolve. Our universe occupies an incredibly narrow window where the value is just small enough to allow for galaxy formation, but just large enough to eventually dominate and drive the acceleration we see today. We don't observe a universe with a wildly different expansion rate because such universes are sterile, devoid of any observers to wonder about their existence. This concept of cosmic selection can feel like a Copernican demotion. We are not at the center of the universe, and our cosmic habitat is not special or centrally planned. It is merely one among countless others, and its properties are the only ones compatible with our own existence. The anthropic principle doesn't explain why the multiverse exists or why the fundamental laws allow for such variation. Instead, it shifts the question, suggesting that the apparent fine-tuning of our universe is not evidence of a designer, but an inevitable selection effect. We are like a fish born in a pond, marveling at how perfectly the water is suited to its gills, without realizing that vast deserts and mountains exist beyond its watery home. It could not survive in those other environments, so of course, from its perspective, the world seems perfectly designed for fish. The challenge, of course, is testability. How can we prove the existence of these other universes if they are forever beyond our observational reach? Proponents argue that the anthropic principle can still make predictions. It predicts, for instance, that any observable fundamental constants that can vary across the multiverse should have values that are typical for universes that produce observers. If we were to discover another such constant that seems finely tuned, and its value falls within the expected anthropic range, it would bolster the idea. The principle remains controversial, with some scientists seeing it as a surrender, a way to avoid seeking a deeper, more fundamental theory that explains our constants from first principles. Others see it as the most honest and logical conclusion to draw from the staggering implications of modern cosmology, a necessary piece of the puzzle that connects our local, bio-friendly reality to the potentially infinite and chaotic whole. Now, let's venture into one of the most radical and mind-bending reinterpretations of gravity itself, a theory that suggests the force which governs the motion of planets and the falling of apples isn't a fundamental interaction at all, but rather an emergent phenomenon, a side effect of the universe's innate tendency toward disorder. This is the theory of emergent gravity pioneered by theoretical physicist Eric Verland. For centuries, since the time of Newton and then refined by Einstein, we've understood gravity as a fundamental force, a basic ingredient of reality. Einstein's genius was to recast it as the curvature of spacetime. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. But what if that curvature, that force, is not a primary feature of the cosmos? What if it's more like the pressure of a gas or the tension on a stretched membrane, a collective behavior that arises from something deeper? This is the core of Verland's proposal. He posits that gravity is an entropic force. To understand what that means, think about the simple, everyday phenomenon of osmosis. If you have a container separated by a semi-permeable membrane with fresh water on one side and salt water on the other, water will spontaneously flow from the fresh side to the saltier side. Why does it do this? It's not being pulled by a fundamental salinity force. The flow is driven by the second law of thermodynamics, the principle that the universe always moves toward a state of higher entropy or greater disorder. The system rearranges itself to maximize the number of possible microscopic configurations, and this statistical tendency manifests as a macroscopic force. Verland argues that gravity is precisely this kind of phenomenon. It's not a fundamental pull, it's the universe's way of maximizing its entropy. In this view, the fabric of space-time and the matter within it are underpinned by a vast, hidden network of microscopic, information-bearing degrees of freedom. We can't see these fundamental building blocks, just as we can't see the individual atoms in a gas, but their collective statistical behavior gives rise to the laws of gravity as we experience them. An object falls to the ground for the same essential reason that molecules diffuse through the air, because it is the path of increasing entropy for the entire system. This idea finds a powerful anchor in the holographic principle we discussed earlier. If our three-dimensional universe is truly a projection of information stored on a two-dimensional boundary, then gravity must also be an emergent property of that data structure. The holographic principle suggests that the maximum amount of information or entropy in any region of space is proportional not to its volume, but to the surface area of its boundary. Verland's emergent gravity naturally incorporates this. When you introduce a massive object into space, it displaces some of this fundamental information, and the natural response of the system to return to a state of maximum entropy manifests as an attractive force, what we call gravity. The mathematics of this process, starting from these first principles of information and entropy, can reproduce Einstein's equations of general relativity without needing to assume gravity as a fundamental force. But the implications become even more profound when we look out at the cosmos. One of the most compelling aspects of emergent gravity is its potential to explain the effects we currently attribute to dark matter. Remember the problem of galaxy rotation curves. Stars at the outer edges of galaxies orbit far too quickly based on the visible matter alone. The standard solution is to add a halo of invisible dark matter. Verland's theory, however, offers a different solution. In his framework, the apparent need for extra matter is an illusion created by a change in the way entropy and information are distributed on cosmic scales. In the low acceleration environment at the outskirts of galaxies, the entropic contribution to the gravitational force changes. The relationship between the energy required to alter the information on the boundary and the resulting force in the volume becomes modified. This modification, derived from first principles about entropy, naturally produces an extra gravitational pull, a pull that perfectly mimics the presence of dark matter without requiring any new exotic particles. The observed radial acceleration relation in galaxies, which tightly links the observed acceleration to the visible mass, emerges naturally from this entropic picture, whereas in the dark matter paradigm, it's a surprising coincidence that requires careful tuning of dark matter halo properties. And what of the universe's accelerating expansion? Could emergent gravity also provide an explanation for dark energy? Verland and others have speculated that the accelerating expansion of the cosmos might be understood as another consequence of the universe's evolving entropy. As the universe expands, the amount of accessible space and the maximum possible entropy increase. This relentless drive toward a state of maximum disorder could manifest as a kind of pressure or repulsive effect on cosmic scales. In this picture, dark energy isn't a mysterious substance or a cosmological constant. It's the thermodynamic response of the cosmos as a whole to its own increasing size and information content. The expansion is the universe naturally relaxing into its state of greatest possible entropy. This is a truly radical rethink. It suggests that the two greatest mysteries in cosmology, dark matter and dark energy, might not be puzzles about missing substances, but rather glaring clues that our understanding of the most familiar force, gravity, is fundamentally incomplete. We've been trying to find the invisible actors on the cosmic stage, when the real story might be about the stage itself and the hidden, informational laws that govern its behavior. Of course, emergent gravity is a very young and highly debated theory. It faces significant challenges, particularly in explaining the intricate patterns of the cosmic microwave background and the precise dynamics of colliding galaxy clusters, where the evidence for a particle like gravitational-only dark matter is very strong. The theory is still under development, and its mathematical framework is being rigorously tested against a mountain of astronomical data. Yet its power lies in its audacious unification. It connects the thermodynamics of black holes, the holographic nature of reality, and the large-scale dynamics of the cosmos into a single, compelling narrative where gravity is not a master force, but a servant to the deeper, more fundamental laws of information and entropy. Now we dive into a theory that takes the concept of infinity and makes it intensely personal, suggesting that every choice you make, every chance event, ripples outward to create entirely new universes. This is the many worlds interpretation of quantum mechanics, and when applied to the cosmos, it paints a picture of reality so vast and prolific that it dwarfs even the grandest multiverse models we've discussed so far. To understand how this connects to the expansion of the universe, we first need to grasp the bizarre quantum problem it was designed to solve. In the tiny world of atoms and particles, things don't behave like billiard balls. An electron isn't in one place at one time. It exists in a cloud of probability, a blend of all possible locations and states described by what physicists call a wave function. Traditionally, when we measure that electron, this fuzzy probability wave is said to collapse into a single, definite outcome. The electron is suddenly here and not there. But what exactly triggers this collapse, the act of observation, human consciousness? This has been a deep and troubling mystery for a century. In the 1950s, a physicist named Hugh Everett proposed a stunningly elegant and radical way out of this conundrum. He suggested that the wave function never collapses at all. Instead, every single possible outcome encoded within the wave function actually happens. When a measurement is made, or indeed when any quantum interaction occurs, the entire universe splits or branches into multiple, non-communicating copies. In one branch, you see the electron in one location. In another, an alternate version of you sees it in a different location. Both outcomes are equally real, but they unfold in separate, parallel realities that decohere from one another, forever diverging. This is the many worlds interpretation. It removes the special role of the observer and paints a reality where all possibilities are realized. Now, let's scale this up from a single electron to the entire cosmos. Imagine the wave function of the universe, a mathematical object that describes the quantum state of everything, every particle, every field, every ripple of spacetime. According to the many worlds view, this universal wave function is constantly, relentlessly branching. Every quantum event that ever occurs, from the decay of a radioactive atom in a distant star to the firing of a neuron in your brain, creates a new fork in the road of reality. The number of parallel universes is not just large, it is mind-numbingly infinite, growing exponentially with every passing moment. So how does this connect to our main theme, the expansion of the universe? The link becomes clear when we consider cosmic inflation, that brief period of hyper-expansion in the very early universe. Inflation was driven by a quantum field, the inflaton field. And like all quantum fields, its behavior was not predetermined, it was governed by probability. As this field evolved, quantum fluctuations, tiny, random variations in its value were occurring everywhere. In the standard story of inflation, these fluctuations got stretched to enormous sizes by the rapid expansion, becoming the seeds for all the large-scale structure we see today, the blueprints for galaxy clusters. But in the many worlds picture, something even more profound was happening. At every single point where a quantum fluctuation could have gone one way or another, the universe branched. This means that the entire inflationary epoch wasn't a single, smooth event, but a foaming, bubbling explosion of reality splitting. In one branch of the wave function, the inflaton field fluctuated in a specific pattern, leading to a universe with a particular arrangement of galaxies and a specific rate of expansion. In another, nearly identical branch, a single quantum fluctuation was different, resulting in a subtly altered cosmic map. And in branches that diverged more significantly, the entire outcome of inflation could be different. Some branches might have experienced a slightly longer period of inflation, creating a universe much larger and emptier than our own. Others might have seen inflation end prematurely, resulting in a cosmos that collapsed almost immediately in a hot big crunch. In the many worlds landscape, there are branches where dark energy is stronger, leading to a rapid big rip, and branches where it is weaker, allowing gravity to eventually halt the expansion. There are even branches where the fundamental constants of nature are different, where protons are unstable or gravity is repulsive. Our universe, with its specific expansion history and its seemingly fine-tuned constants, is just one thread in an infinite tapestry of cosmic possibilities. We don't inhabit a special universe, we simply inhabit a branch compatible with our existence, a concept that resonates deeply with the anthropic principle. This interpretation also raises a fascinating, though highly speculative, question. Could the branching process itself have a gravitational effect? Could the ongoing proliferation of parallel realities, the continuous unzipping of the universal wave function, exert a subtle influence on the dynamics of space-time within each branch? Some theoretical physicists have explored whether the quantum potential of the wave function, a term in the equations that guides particle trajectories, could play a role in the large-scale behavior of the cosmos. While this is a fringe idea, it points to a breathtaking possibility that the expansion of our universe and the expansion of the multiverse of possibilities might be two sides of the same coin, both driven by the relentless and creative evolution of the quantum wave function. The many worlds interpretation offers a vision of cosmic expansion that is both internal and external. Not only is the space within our branch stretching, but the entire tree of reality is constantly growing new branches, each one a full-fledged universe with its own unique cosmic destiny. It suggests that infinity is not just a feature of our future, but a characteristic of our present, being generated at every moment, in every quantum decision forever. But what if the ultimate cosmic nesting doll exists not in parallel brains, but within the most enigmatic objects we know? Let's venture into a theory that suggests our entire universe, in all its vastness, might be the interior of a black hole residing in a much larger parent cosmos. This is the speculative but captivating idea of black hole cosmology. At its heart, this model proposes a stunningly elegant solution to the mystery of the Big Bang's initial singularity. In our standard model, the universe began from a point of infinite density where our laws of physics break down. But from the perspective of an observer outside a black hole, matter falling in appears to slow down and freeze at the event horizon due to time dilation, never actually reaching the central singularity from their point of view. Some physicists like Nikodem Poplawski have taken this concept and run with it, suggesting that the interior of a black hole, as described by the equations of general relativity, can be mathematically equivalent to an expanding universe. In this picture, the Big Bang was not the beginning of everything, but rather the bounce or the inflationary beginning of a new space-time region inside a black hole that formed in a pre-existing universe. Imagine a massive star in this parent universe collapsing into a black hole. From our external perspective, we see an event horizon form. But from the perspective of someone or something falling through that horizon, the geometry of space-time is drastically different. The roles of space and time can swap, and the central singularity doesn't lie in the future, but in the past, acting as the point-like, high-density origin for a new, expanding cosmos within. This would naturally account for the initial hot, dense state we call the Big Bang without requiring a true, physics-breaking singularity from nothing. The expansion we observe all around us, then, is simply the continued growth of this interior region. But how does this connect to the holographic principle we explored earlier? The link is profound and provides a potential mechanism for this entire process. The holographic principle tells us that all the information describing a volume of space can be encoded on its boundary. For a black hole, that boundary is the event horizon. The information about everything that falls into a black hole is not lost inside, but is stored as a hologram on its two-dimensional surface. Now apply this to the black hole cosmology model. If our universe is the interior of a black hole, then the boundary of our observable universe, the spherical limit from which light has had time to reach us, could be analogous to that event horizon. In this view, the entire three-dimensional reality we experience, with its hundreds of billions of galaxies, is a holographic projection of quantum information encoded on our cosmic boundary. This provides a breathtakingly unified picture. The expansion of our universe could be understood as new information being added to this cosmic hard drive. As the parent universe evolves, or as more matter falls into our host black hole from its perspective, our event horizon grows, and the information content on our boundary increases, which we perceive from the inside as the relentless stretching of space and the creation of new volume. This model even offers a potential explanation for the early universe's rapid inflation. The initial frantic growth could correspond to the violent, dynamic process of the black hole's formation and the subsequent settling of its horizon. So, could we ever test such a fantastical idea? While it seems inherently untestable, physicists have proposed some potential observational signatures. One key area of investigation is the cosmic microwave background. The CMB is the oldest light we can see, a fossilized snapshot of the young universe. Its pattern of tiny temperature fluctuations holds a wealth of information about the initial conditions. Some models of black hole cosmology predict that the specific statistical properties of these fluctuations, their so-called non-Gaussianities, would have a unique fingerprint different from those predicted by standard inflation. Furthermore, the overall geometry of our universe might carry an imprint. If we live inside a black hole, the geometry of our cosmos might have a specific type of slight curvature or a particular topology that could, in principle, be measured by future, ultra-precise maps of the CMB or by studying the large-scale distribution of galaxies. Another potential test lies in the nature of gravity itself. In some formulations, the effective gravitational force within a black hole universe could exhibit subtle deviations from Einstein's predictions on the very largest scales, which might one day be detectable through precise measurements of the universe's expansion history. While these ideas are highly speculative and far from the mainstream, they represent a powerful drive in theoretical physics to connect the largest and smallest scales of reality. The black hole cosmology and its holographic underpinnings challenge our most basic assumptions about location and reality, suggesting that the cosmos we call home might just be one intricate piece of an infinitely recursive and holographic chain of realities. From the bizarre quantum branching of the many worlds interpretation, we now turn to a theory that questions another seemingly unshakable pillar of physics, the very strength of gravity itself. What if the force that binds the cosmos isn't a fixed, eternal constant, but a number that has been slowly changing over the vast eons of cosmic history? This is the intriguing proposal behind a time-varying gravitational constant, often denoted by the letter G. In Sir Isaac Newton's law of universal gravitation, and later in Einstein's theory of general relativity, G is treated as a fundamental, unchanging number that sets the strength of the gravitational pull between all masses. It's a cornerstone of our physical models, assumed to be the same here on Earth, in distant galaxies and across all of time. But what if this cornerstone is slowly eroding or perhaps strengthening? This idea isn't new. One of the first prominent scientists to seriously consider a changing G was the Nobel laureate Paul Dirac. In the 1930s, Dirac was struck by what he called large number coincidences. He noticed that certain ratios of fundamental constants, when combined, produced immense numbers that were curiously similar in magnitude. For instance, the ratio of the electrostatic force to the gravitational force between a proton and an electron is a number with about 40 digits. Intriguingly, the age of the universe expressed in fundamental time units is another number with a similar, vast scale. To Dirac, this couldn't be a mere accident. He proposed his large number hypothesis, suggesting that these coincidences were evidence of a deep connection between the microcosm of particles and the macrocosm of the universe. A natural consequence of this hypothesis was that the gravitational constant G must be inversely proportional to the age of the universe. In other words, as the cosmos grows older, the force of gravity grows progressively weaker. This was a radical departure from established thought, implying that the laws of physics were not fixed but evolved alongside the expanding cosmos. If gravity was stronger in the past, it would have profound implications for the universe's expansion history. A stronger gravitational pull in the early universe would have acted as a more powerful brake on the initial expansion from the Big Bang. This could potentially alter our interpretation of the cosmic timeline and the formation of large-scale structures. More recently, the idea of a varying G finds a natural home in a class of theories known as scalar tensor theories of gravity. These are extensions of Einstein's general relativity that introduce an additional field, a scalar field that permeates all of space, which couples to gravity and effectively makes the gravitational constant a dynamic quantity, a function of that field. In these frameworks, the value of G can change with time and location, driven by the evolution of this cosmic scalar field. The connection to our modern cosmological puzzles is immediate and compelling. Could a slowly declining gravitational constant be masquerading as dark energy? If the strength of gravity were gradually diminishing over billions of years, its ability to pull the universe back together would be weakening. From our perspective, this would look exactly like a new, repulsive force starting to dominate and push galaxies apart at an accelerating rate. In this scenario, the cosmic acceleration we measure isn't caused by a mysterious dark energy, but is instead an illusion created by the fading power of gravity itself. This offers an elegant alternative, unifying the two great forces shaping our cosmic fate: the expansion driven by the Big Bang's initial impetus and the apparent acceleration, into a single, evolving framework governed by a single changing constant. Of course, such a profound claim requires equally profound evidence, and so far, the universe has been reluctant to provide it. Scientists have devised incredibly precise methods to test whether G is truly constant. One of the most famous experiments involves lunar laser ranging. Since the Apollo missions left retroreflectors on the moon, astronomers have been firing lasers at them and timing the light's return trip. By measuring the precise distance to the moon over decades, they can detect any tiny change in the gravitational interaction between the Earth and the moon that would be caused by a varying G. After more than 50 years of data, the results are starkly clear. Any change in the gravitational constant must be extraordinarily small, limited to less than 1 part in a trillion per year. Similarly, the process of Big Bang nucleosynthesis, which forged the first light elements like hydrogen, deuterium, and helium in the first few minutes of the universe, provides a powerful probe of the early cosmos. The abundances of these elements are exquisitely sensitive to the expansion rate of the universe during that first, fiery burst of nuclear fusion. The expansion rate, in turn, depends on the strength of gravity. When we compare the observed cosmic abundances of these light elements with the predictions from nucleosynthesis models, they agree remarkably well, but only if the gravitational constant was very nearly the same then as it is now. This places another tight constraint on how much G could have varied over the last 13.8 billion years. So where does this leave the theory? The stringent observational limits have largely ruled out the simplest models, like Dirac's original proposal of a G that decreases inversely with the age of the universe. Such a large variation would have left unmistakable imprints that we simply do not see. However, the door is not completely closed. More sophisticated scalar tensor theories can be constructed where the variation of G is extremely slow, or where it was more significant in the very early universe but has since stabilized, or where the variation happens in a way that subtly influences cosmic acceleration without violating the bounds from the solar system or nucleosynthesis. The quest to measure G with ever greater precision continues, as even a tiny, slow variation could force a major revision of our understanding of gravity and provide a beautifully minimalist solution to the dark energy puzzle, all by allowing one of the universe's most fundamental numbers to have its own quiet history. But if our imagination has been stretched by the idea of a universe born from a black hole, then prepare to question the very fabric of reality itself. We are about to explore a theory that suggests the smooth, continuous spacetime described by Einstein is nothing more than a convincing illusion, a kind of cosmic smoothie blended from the most fundamental ingredients imaginable. This is causal set theory, a provocative approach to quantum gravity that proposes spacetime is not a smooth continuum, but is instead granular, composed of finite, discrete building blocks. Think of the world around you. A wooden table appears solid and continuous, but we know it is actually made of a vast collection of discrete atoms. Causal set theory argues that spacetime itself is no different. At the tiniest possible scale, the Planck scale, the universe is not a seamless fabric, but a vast collection of individual atoms of spacetime. These fundamental elements are not points in space, they are space and time in their most basic form. What gives this collection its structure and allows it to behave like the space-time we know is not its location, but something more fundamental, causality. The theory posits that these space-time atoms are partially ordered by a relationship of cause and effect. If one event, one atom, can influence another, then they are causally linked. The entire history of the universe, from the Big Bang to this very moment, can be thought of as a vast, growing network of these causal relationships, a causal set. This perspective turns our conventional view of physics on its head. In Einstein's universe, space-time is the primary stage, and particles and forces are the actors moving upon it. But in causal set theory, the causal relationships between events are the primary reality. The geometry of space and the flow of time are secondary, emergent properties that arise from the intricate web of these cause and effect connections. It's a universe built not on location but on influence. Now you might wonder, how does such a discrete, chunky spacetime appear so perfectly smooth to us? The answer lies in a process known as coarse graining. Imagine looking at a television screen from just inches away. You would see the individual, discrete pixels that make up the image. But if you step back across the room, those pixels blend together into a smooth, continuous picture. In the same way, the fundamental pixels of spacetime are so incredibly fine-grained, trillions of times smaller than an atom, that at our everyday scale, and even at the scale of galaxies, the universe appears perfectly smooth and continuous. Our scientific instruments simply aren't sharp enough to see the individual grains. So, how does this radical rethinking of spacetime's nature impact our understanding of the universe's infinite expansion? The implications are profound. First, causal set theory offers an elegant escape from the dreaded singularities that plague general relativity. The Big Bang singularity, that point of infinite density, is a clear signal that Einstein's equations break down. But in a discrete causal set, you cannot have an infinite number of spacetime atoms in a single point. The very idea is meaningless. Instead, the beginning of our universe would be represented by a single foundational spacetime atom, or a very simple, finite set of them. The Big Bang wasn't an explosion from an infinitely dense point, but the first moment of a causal chain that has been growing and evolving ever since. The expansion of the universe, in this view, takes on a completely new character. It is not the stretching of a smooth, rubber sheet fabric. Rather, it is the continual, spontaneous growth of new spacetime atoms. Think of it as a cosmic crystal constantly adding new units to its structure. The rate and pattern of this growth, how many new atoms are born and how they connect to the existing causal network, would determine the large-scale evolution of the cosmos. This provides a potential pathway to explain the accelerating expansion without needing to invoke a mysterious dark energy. Perhaps the acceleration is not due to a repulsive force, but is a natural consequence of the underlying dynamics of the causal set itself. Maybe, as the set grows larger, the statistics of its growth naturally lead to an exponential increase in the number of new spacetime atoms being generated, which we measure from within the system as an accelerating expansion. Some models within the theory suggest that the cosmological constant, the simplest form of dark energy, could emerge directly from the random, Poisson-like process of new element creation in the causal set. The theory is still in its developmental stages, facing significant mathematical and conceptual challenges. One of the biggest is the reconstruction problem, of figuring out exactly how the familiar four-dimensional spacetime of general relativity, with its specific curvature and dynamics, emerges reliably from the abstract, order-theoretic structure of a causal set. It's like trying to derive the entire, rich experience of a flowing river from nothing but a list of which water molecules have bumped into which others. Yet the promise of causal set theory is immense. By starting with a discrete causal foundation, it attempts to build a universe where gravity and quantum mechanics are not forced together, but arise naturally from the same fundamental principles. It suggests that the infinity we see in our equations is merely a mathematical convenience, and that the true, underlying cosmos is finite, granular, and built one causal connection at a time. But to truly challenge our perception of reality, we must consider a possibility where the very arrow of time, the one-way flow from past to future that we all experience, is not a universal absolute but a local feature of our cosmic domain. This brings us to a profoundly elegant and mind-bending hypothesis: the existence of a mirror universe, a parallel cosmos born in the same fiery instant as our own but evolving backwards in time. The foundation for this astonishing idea lies in one of the most sacred principles in physics, known as CPT symmetry. CPT stands for charge, parity, and time. The principle states that the laws of physics should be perfectly symmetric if you were to simultaneously reverse three things. Replace every particle with its antiparticle charge reversal, view the universe in a mirror parity reversal, and reverse the flow of time-time reversal. Imagine a film of a particle interaction. If CPT symmetry holds, the film should look physically plausible whether you run it forward or backward, as long as you also flip the charges and view it in a mirror. For every interaction we've ever observed, this profound symmetry has held true. It is considered a fundamental, unbreakable cornerstone of quantum field theory. However, when we look at our universe on its own, we see clear violations of the individual components. For instance, certain rare particle decays show a preference for a specific handedness, violating parity symmetry. More famously, the cosmos is overwhelmingly made of matter, with very little antimatter, a blatant violation of charge symmetry. And of course, we experience a strong arrow of time, where entropy always increases, violating time symmetry on a macroscopic scale. Our universe in isolation is not CPT symmetric. So, if CPT symmetry is so fundamental, but our universe clearly isn't, where did the symmetry go? The brilliant resolution proposed by physicists like Neil Turok and others is that the symmetry isn't broken, it's just hidden. The Big Bang did not create a single universe. It created a pair of universes, our own and a mirror twin. In our universe, time flows forward and matter dominates. In the mirror universe, time flows backward from our perspective and antimatter dominates. When you consider both universes together as a single, coupled system, the full CPT symmetry is restored. The mistakes in our universe are perfectly counterbalanced by the opposite mistakes in the mirror world. From the perspective of a god-like observer outside both, the entire system is perfectly symmetric and elegant. Now, what would such a mirror universe be like? It's not simply a world where people walk backward and talk in reverse. From the perspective of an observer within that universe, their time would feel just as normal and forward-flowing as ours does to us. They would remember their past and anticipate their future, but their past would be our future and vice versa. From the moment of the Big Bang, the two universes evolved in opposite temporal directions. In the first instant, they were in perfect thermal contact, a state of maximum entropy. As they evolved away from each other in time, the entropy in both universes increased, satisfying the second law of thermodynamics from both perspectives. This is not science fiction. It is a serious, albeit speculative, attempt to resolve one of the deepest asymmetries in our physical laws. The implications for cosmic expansion are immediately fascinating. Could the gravitational influence of this mirror universe be affecting the dynamics of our own? One compelling proposal is that the dark matter that holds galaxies together might not be an exotic new particle at all, but could simply be the collective gravitational pull of ordinary stars and planets in the mirror universe. Because the mirror world is made of antimatter from our point of view, its particles would not interact with our light or our matter via any force except gravity. It would be completely dark and transparent to us, yet its mass would exert a gravitational tug, exactly as dark matter is observed to do. In this picture, every galaxy in our universe could be paired with a mirror galaxy, their stars and planets overlapping in space but forever separate in time, their combined gravity providing the extra pull that explains the rapid rotation of galaxies without any need for invisible matter in our own realm. This offers an incredibly elegant and minimalist solution to the dark matter puzzle. Furthermore, the interaction between these two universes could have subtle effects on the expansion rate itself. Some models suggest that a weak quantum connection, a form of entanglement across the temporal divide, might persist. This residual link could manifest in the behavior of the most elusive of particles, neutrinos. Neutrinos are famous for their ability to oscillate, to transform from one type into another as they travel. It has been hypothesized that this oscillation could, in part, be influenced by interactions with their mirror counterparts. If we were to detect anomalies in neutrino oscillations that cannot be explained by standard physics, it could be a faint, whispering signal from the other side of time, a ghostly handshake from our cosmic twin. While detecting a universe that is causally disconnected from us in time is a monumental challenge, the quest to find evidence for this idea continues. The mirror universe hypothesis forces us to confront our deepest assumptions about time, matter, and the very nature of a beginning. It suggests that our expanding cosmos is just one half of a grander, more symmetric whole, a dance of two realities born from a single, balanced act of creation, forever moving in opposite directions but forever linked by the invisible threads of fundamental symmetry. Now, let's turn to a theory that takes the holographic principle to its ultimate and perhaps most unsettling conclusion: the idea that our entire cosmos, with its billions of galaxies and its accelerating expansion, might not be a fundamental reality at all, but rather an incredibly sophisticated simulation, a kind of cosmic virtual reality running on some sort of unimaginable computer. This is the simulation hypothesis, and it forces us to confront deep questions not just about the nature of the universe, but about the nature of existence itself. The foundation for this idea doesn't come from science fiction, but from a convergence of several threads in modern physics. We've already explored the holographic principle, which suggests that all the information describing a three-dimensional volume of space can be encoded on a two-dimensional boundary. This is strikingly similar to how a modern 3D video game works. The rich, immersive world you see on your screen isn't stored as a full, three-dimensional reality inside your computer. It is rendered in real time from a set of underlying code and data, projected from a two-dimensional graphics card onto your three-dimensional seeming display. If the holographic principle is correct, our universe operates on a similar principle, with the three-dimensional world we experience being a projection from a two-dimensional surface at its boundary. This immediately raises a tantalizing question. If our universe can be described by information on a surface, what is processing that information? The simulation hypothesis takes this one step further by suggesting that this processing isn't happening on some abstract cosmological boundary, but on a computer of sorts in a wider parent reality. The logic often cited in favor of this idea is a statistical one. If it is possible for an advanced civilization to create realistic simulations of entire universes, simulations so complex that the simulated beings inside them become conscious and are unaware of their simulated nature, then over the vastness of cosmic time, the number of such simulated universes would vastly outnumber the one base physical reality. Therefore, by sheer probability, it is more likely that we are living in one of those countless simulations than in the original reality. This is a modern, technological twist on the old philosophical brain in a vat thought experiment. But how could such a simulation work, and what would it mean for the expansion of the universe? Think about the computational resources required. Simulating every single atom in real time would be impossibly demanding, even for a hyper-advanced civilization. However, a clever simulation wouldn't need to do that. It would only need to render the parts of the universe that are being observed, much like a video game only renders the part of the game world that is currently on your screen. This concept in computing is called level of detail. From this perspective, the laws of physics, including the speed of light, might not be fundamental constants of nature, but rather processing limits built into the simulation's architecture. The speed of light could be the maximum processing speed of the cosmic computer, the rate at which information can be updated across the simulation's grid. The quantum weirdness we observe, where particles exist in a blur of probability until measured, could be a form of data compression. The simulation only calculates a definite state for a particle when it absolutely has to, when an observation is made in order to save on processing power. This brings us directly to the universe's accelerating expansion. If our universe is a simulation, its expansion could be a programmed feature. Perhaps the simulation has a set runtime or a specific end state it is designed to reach, and the accelerating expansion is simply the execution of that part of the code. The cosmological constant, lambda, that we've identified as the driver of dark energy might not be a mysterious energy of the vacuum, but a simple parameter in the simulation's equations of state, a variable set by the programmers to see how a universe with that specific expansion rate unfolds. Some thinkers have even speculated that the acceleration could be a sign of the simulation's increasing computational load. As the universe expands, more space is created, which requires more memory and processing cycles to maintain. The acceleration could be a symptom of the system struggling to allocate resources, or perhaps a deliberate simplification of the physics in the far future as the simulation's focus shifts. The most fascinating question, of course, is whether we could ever find evidence for this. Could we detect a glitch in the matrix? Scientists and philosophers have proposed a few possibilities. One place to look is in the fundamental laws themselves. Are there signs of approximation or rounding errors? For instance, the physical constants, like the fine structure constant that governs the strength of electromagnetic interactions, are seemingly arbitrary numbers. If we found that these constants were simple mathematical ratios or computable numbers, it might hint at a designed system. Another place to look is in the very high energy regimes of particle physics. If spacetime is indeed a discrete lattice at the tiniest Planck scale, as suggested by some quantum gravity theories, we might one day see evidence of this pixelation. Just as a digital image breaks down into individual pixels when you zoom in too far, ultra-high-energy cosmic rays might behave in ways that reveal the underlying grid of the simulation. Perhaps the most famous proposal is to look for shortcuts or optimizations in the laws of physics. The simulation might use simplified versions of physics in situations that are rarely observed. Any inconsistency we find, any law that seems to break down in a way that suggests computational saving, could be a tantalizing clue. The philosophical implications of this idea are staggering. It challenges our concepts of free will, consciousness, and reality. If we are in a simulation, are our thoughts and choices our own, or are they simply the output of a deterministic algorithm? Does it make our lives and struggles less meaningful, or perhaps more meaningful as part of a grand cosmic narrative? The simulation hypothesis sits at the blurry boundary between metaphysics and physics. While it is not a testable scientific theory in the traditional sense, it serves as a powerful conceptual tool, forcing us to question the nature of the reality we take for granted and to see the profound connections between information, computation, and the cosmos. It suggests that the ultimate truth of our expanding universe might not be found in a telescope, but in the fundamental language of code from which it is rendered. Now, let's consider a truly foundational question about the nature of inertia itself. Why does an object resist being accelerated? What is the origin of that stubborn property we call mass? The common sense answer might be that it's just an intrinsic property of matter, but some of the greatest minds in physics have wondered if there's a deeper cosmic connection at play. This line of thinking leads us directly to a principle first articulated by the philosopher Ernst Mach. Mach's principle proposes that the inertia of an object, its resistance to motion, isn't an inherent property at all. Instead, it arises from the gravitational influence of all the other matter in the universe. Think of a single spinning gyroscope in an otherwise empty cosmos. In a Newtonian view, it would still have inertia, but Mach argued that in a truly empty universe, the concept of inertia would be meaningless. The gyroscope's resistance to being turned comes from its interaction with the distant stars and galaxies. Their collective mass defines the fixed background against which acceleration is measured. It's a beautiful, holistic idea that the local is defined by the global. Albert Einstein was deeply inspired by this concept, and he sought to incorporate it into his theory of general relativity. While general relativity does contain some Machian elements, for instance, the dragging of spacetime by rotating masses, it doesn't fully realize Mach's vision. In Einstein's theory, an object would still possess inertia even in a completely empty universe. This has led some physicists to explore theories that more completely embody Mach's principle, and one of the most intriguing is the self-creation cosmology. This theory, developed by physicists like Garth Barber, takes a bold step by modifying the very bedrock of general relativity. It proposes that the universe is not a closed system where matter and energy are strictly conserved. Instead, the theory allows for the continuous creation of matter and fields from the gravitational field itself. In this picture, the universe isn't just expanding, it is actively growing its own substance as it evolves. The driving engine for this is a scalar field, similar in some ways to the inflaton or quintessence fields we've discussed, but with a unique role. This field couples to matter, and its evolution dictates the rate at which new mass is created. This has a breathtaking consequence. The masses of particles are not constant. Over the vast eons of cosmic history, the mass of an electron or a proton would be slowly, imperceptibly increasing. This is a radical departure from standard physics, where particle masses are considered fundamental constants. So, how could this possibly explain the observed expansion of the universe without dark energy? The connection is elegant. In self-creation cosmology, the creation of new matter is intrinsically linked to the expansion of space. As the universe grows, new matter is generated, and this process feeds back into the geometry of spacetime, driving the expansion forward. The observed acceleration isn't caused by a repulsive dark energy, but is a natural outcome of this cycle of self-creation. The universe is quite literally bringing itself into being as it expands, with the force we call dark energy being an illusion, a misinterpretation of this underlying cosmic genesis. This framework also offers a novel pathway toward unifying gravity with quantum mechanics. By making mass a variable quantity tied to a dynamic field, it blurs the line between the fabric of space-time and the particles that reside within it. Gravity is no longer just the curvature of space-time caused by mass. It is also the mechanism by which mass itself is generated. This creates a feedback loop where matter tells space-time how to curve, and the evolving curvature of space-time tells matter how much mass to have. It's a profoundly interconnected view of reality, where the universe and its contents co-create each other in a continuous dance. Of course, such a profound revision of physics must make testable predictions that distinguish it from the standard model. One key prediction involves the precise rate of the universe's expansion throughout its history. Self-creation cosmology predicts a specific, slightly different expansion history compared to the lambda-CDM model, which could be tested with increasingly precise observations from telescopes like the James Webb Space Telescope as they map the cosmos across different epochs. Another crucial test involves the cosmic microwave background. The specific patterns of hot and cold spots in this primordial light are a sensitive probe of the universe's early conditions and its composition. The presence of a dynamic scalar field that alters particle masses would leave a distinct imprint on these patterns, an imprint that future ultra-high-precision maps of the SIMB could potentially reveal or rule out. Furthermore, if particle masses are slowly increasing, this would have subtle effects on the atomic spectra of distant galaxies. As we look back in time at ancient quasars, we might observe tiny shifts in the wavelengths of specific atomic lines that cannot be explained by the standard redshift due to expansion alone. While current observations have not found evidence for such variations, they continue to place ever tighter constraints on the theory. The appeal of self-creation cosmology lies in its philosophical elegance and its potential for unification. It offers a universe that is truly self-contained and self-generating, fulfilling a deep Machian intuition that local physics is dictated by the cosmic whole. It challenges our most basic assumptions about conservation laws and constants, suggesting that the universe is a more dynamic and creatively unstable place than we ever imagined, perpetually giving birth to itself in an act of continuous creation. But just when we think we have a handle on the grand, uniform picture of our isotropic cosmos, a strange and persistent set of clues emerges from the data, whispering that the universe might have a preferred direction after all. This brings us to a truly perplexing mystery embedded in the most pristine map of the early universe, the so-called axis of evil. The cosmic microwave background radiation is our most powerful tool for understanding the infant cosmos. It should be, according to the standard model, a nearly perfect Gaussian random field, meaning its tiny temperature fluctuations should be scattered randomly across the sky with no preferred axis or alignment. It should be the ultimate example of cosmic democracy, with no direction being special. However, when scientists began analyzing the full sky maps from the WMAP and later the Planck satellites, they noticed something deeply unsettling. The largest scale fluctuations in the CMB, the ones that span the entire observable universe, appear to be aligned along a particular axis in space. It's as if the universe has a faint but definite equator and poles. Even more strangely, this apparent axis seems to be aligned, with a probability that seems far beyond mere chance, with the plane of our own solar system and the direction in which we are moving through the cosmos. This unexpected correlation between the very largest scales of the universe and our local, insignificant neighborhood is what earned the phenomenon its dramatic nickname, the axis of evil, because it so flagrantly violates the Copernican principle that we do not occupy a special place in the cosmos. The implications of this are staggering. If this alignment is real and not a statistical fluke, it suggests that the universe's expansion might not be perfectly isotropic or the same in all directions. Instead, we could be living in a cosmos with a subtle but fundamental anisotropy, a preferred direction on the grandest of scales. This would mean that dark energy's push or the very fabric of spacetime itself might be slightly stronger in one direction than in others, leading to a universe that is stretching in a lopsided way. One compelling theory that could account for such a phenomenon involves the presence of a pre-existing, ultra-large-scale structure that predates inflation. Imagine if the patch of spacetime that inflated into our observable universe was not perfectly uniform to begin with. Perhaps it possessed a slight directional stretch, a kind of cosmic grain, much like the grain in a piece of wood. When inflation blew that tiny patch up to an unimaginable size, it would have stretched that initial anisotropy across the entire sky, imprinting it onto the cosmic microwave background as the axis of evil we potentially observe today. This pre-inflationary grain could be a relic of a more complex origin, a fingerprint of the quantum gravity epoch, or even a previous phase of a cyclic universe. Another fascinating possibility involves topological defects in the fabric of spacetime. In the frantic energy of the early universe, as fundamental forces were splitting from one another, it's possible that cracks or imperfections formed in the cosmos, similar to the cracks that form in ice as water freezes. One such defect is a cosmic texture, a knot in the fields that fill the universe. If such a texture existed on a scale larger than our observable universe, its gravitational influence could create a peculiar motion, a bulk flow, tugging our entire galactic neighborhood in a specific direction. This preferred flow would then align with the CMB anomalies, creating the eerie correlation we see. The gravitational pull of such an immense structure would literally be dragging us, and the axis we detect would point directly toward it. The debate over the axis of evil is one of the most intense in modern cosmology. Skeptics argue forcefully that the anomalies are simply a statistical illusion. When you look at any complex dataset, especially one as rich as the CMB, you are bound to find some patterns that look unusual purely by chance. They point out that the significance of the alignment decreases when certain foreground effects from our own Milky Way galaxy are more carefully subtracted. Furthermore, the Planck satellite's higher precision data, while not erasing the signal entirely, has made it somewhat less pronounced, allowing many cosmologists to maintain that it is likely a compelling but ultimately random fluke. They caution against overthrowing the foundational principle of isotropy based on what could be cosmic pareidolia, seeing faces in the clouds of the early universe. However, the persistence of the signal across multiple missions keeps the door open. If future observatories, perhaps measuring the polarization of the CMB with even greater fidelity, were to confirm that these alignments are indeed a real feature of the primordial universe, it would necessitate a revolutionary shift in our thinking. We would have to rewrite our models of inflation and cosmic evolution to incorporate a fundamental directionality, a cosmic north that guides the expansion of everything. It would mean our universe is not a perfectly smooth and featureless balloon, but one with a subtle warp, a fundamental lopsidedness written into its first light, challenging our most deeply held assumptions about the cosmos and our place within it. What if the two greatest mysteries of the cosmos, dark matter and dark energy, weren't two separate entities at all, but rather two different faces of a single exotic substance? This is the fascinating proposition behind the Chaplygin gas model, a concept that dares to unify the dark sector into one all-encompassing, unified dark fluid. Imagine a cosmic chameleon, a fluid whose properties transform dramatically over the lifetime of the universe. In the dense, crowded conditions shortly after the Big Bang, this fluid would have clumped together under gravity, providing the gravitational scaffolding necessary for galaxies to form, behaving exactly like the dark matter we infer. Then, as the universe expanded and thinned out, this same fluid would have undergone a phase change, developing a strong negative pressure that drives galaxies apart at an accelerating rate, mimicking the dark energy we observe today. The original inspiration for this idea comes from an unlikely place, aerodynamics. In the early 20th century, a Russian scientist named Sergei Chaplygin was studying the lift on an aircraft wing and derived an equation of state for a hypothetical gas where pressure is inversely proportional to density. In a cosmological context, this exotic fluid has an equally exotic property. Its pressure doesn't just drop as the universe expands. It becomes more and more negative, acting as a kind of cosmic tension that eventually overwhelms gravity and kicks the expansion into high gear. Think of it like a strange cosmic glue that first acts as a binding agent, holding cosmic structures together. And then, as it ages and the universe stretches, it begins to act as a repulsive force, pushing everything apart. The beauty of this model is its stunning simplicity and elegance. Instead of two completely unknown components making up 95% of the universe, we would have just one. This single dark fluid would have dominated the cosmic budget throughout history, its identity shifting seamlessly from a clustering, matter-like state to a smooth, energy-like state as the cosmos evolved. This transition provides a natural explanation for why the acceleration of the universe is such a recent phenomenon in cosmic terms. For billions of years, the fluid's matter-like behavior was dominant, allowing gravity to pull matter into the vast cosmic web. Only when the universe had expanded enough and the density of this fluid dropped below a critical threshold did its dark energy persona emerge to take control of the cosmic destiny. Of course, the original Chaplygin gas model is a starting point, and physicists have developed more sophisticated variations to better match the data. One of the most prominent is the generalized Chaplygin gas, which introduces an extra parameter, alpha, that gives the model more flexibility in how the pressure and density relate to each other. When alpha equals 1, we recover the original model. When alpha equals 0, the fluid behaves almost exactly like a standard cosmological constant. This allows the theory to be finely tuned and tested against a barrage of astronomical observations. The true test for any unified model lies in its ability to explain the full suite of cosmological evidence. For instance, the model must account for the precise patterns seen in the cosmic microwave background. The locations and sizes of the hot and cold spots in this ancient light are a sensitive probe of the universe's composition and the behavior of its components. A fluid that transitions from behaving like matter to behaving like energy leaves a distinct signature on these patterns, and early comparisons showed some tension, as the original model struggled to simultaneously fit the CMB data and the observations of distant supernova that revealed the acceleration. Furthermore, the way galaxies cluster on large scales provides another critical test. Dark matter's ability to clump is essential for forming the intricate filamentary structures we see in the universe. A unified fluid must be able to mimic this clumping behavior perfectly in the early universe. Some versions of the Chaplygin gas model have faced challenges here, as the fluid can develop sound waves that prevent the small-scale clustering needed to form the first galaxies, a problem not faced by simple, collisionless dark matter. Despite these hurdles, the quest for a unified dark fluid remains an active and compelling area of research. It represents a powerful drive in theoretical physics to find simpler, more fundamental explanations for the cosmos's behavior. The ongoing search involves looking for specific, subtle imprints that such a fluid would leave on the distribution of galaxies or the way gravity lenses light from distant quasars. While the current data from probes like the Planck satellite and large-scale galaxy surveys strongly favor the standard lambda CDM model with its two separate dark components, the Chaplygin gas model stands as a brilliant and elegant alternative, a testament to the creativity of cosmologists striving to peel back the layers of our universe's deepest secrets. But if the vacuum of space is truly a seething foam of quantum energy, as our theories suggest, then we are confronted with arguably the most frustrating and profound mismatch in all of physics, the cosmological constant problem. The amount of vacuum energy predicted by quantum field theory is a number so staggeringly large it defies comprehension. It should be one followed by 120 zeros larger than the tiny, gentle value we actually observe for dark energy. It is the worst prediction in the entire history of science, a miscalculation so vast it's like calculating the weight of the entire planet Earth and getting an answer that suggests it should weigh less than a single feather. If the quantum vacuum energy really gravitated with its full predicted strength, the repulsive force would have been so unimaginably powerful that it would have ripped every atom, every nucleus, and the very fabric of space-time to shreds in the first instant after the Big Bang. The fact that we exist at all means something is profoundly wrong with our understanding, or something is miraculously right with the universe. This glaring contradiction is the cosmological constant problem, and solving it has driven physicists to consider some of the most radical ideas imaginable, including theories that suggest the vacuum energy might not gravitate at all. One of the most compelling of these modern approaches is known as vacuum energy sequestering. The core idea is as simple as it is revolutionary. Perhaps the universe has a built-in mechanism that prevents the colossal energy of the quantum vacuum from contributing to the curvature of space-time. Imagine you have a car with an incredibly powerful, roaring engine, but it's equipped with a sophisticated clutch that completely disengages that engine from the wheels. The engine is still running, full of energy and potential, but it's not making the car move. Vacuum energy sequestering proposes a similar cosmic clutch for gravity. The quantum vacuum can buzz and bubble with all the energy it wants, but a global mechanism ensures that this specific form of energy does not couple to gravity. It simply doesn't weigh anything. This would solve the problem at its root. The terrifyingly large vacuum energy predicted by quantum theory would be effectively neutralized, rendered gravitationally inert, and therefore incapable of blowing the universe apart. But this then raises an even more delicate question. If the vacuum energy doesn't gravitate, then what is causing the gentle, accelerated expansion we actually measure? Where does the small but non-zero value of dark energy come from? The theory proposes that the observed cosmological constant isn't the vacuum energy itself, but something else entirely, a separate, intrinsic curvature of the universe that is determined by its entire history and topology. It's a kind of residual background curvature that exists independently of the frantic quantum jitters in the vacuum. The mechanism for this decoupling is where things get truly fascinating, often invoking concepts that sound like they're from the edge of physics. One such idea is the gravitational ether. Now, this isn't the luminous ether of 19th century physics that light was thought to wave through. This is a modern, hypothetical substance or a property of spacetime itself that acts as a medium to absorb or neutralize the gravitational effect of vacuum energy. Think of it like a cosmic sponge. The immense pressure of the quantum vacuum is poured into this sponge, but the sponge itself doesn't transmit that pressure to the gravitational field. It sequesters it, isolates it. In some formulations, this ether is a field that pervades all of space, modifying the way gravity works on the largest scales to effectively ignore the vacuum fluctuations. In others, it's a consequence of imposing a global constraint on the universe, a rule that the average value of the cosmological constant over all of space-time must be zero, forcing a cancellation that leaves behind only the small, observed residual we call dark energy. The appeal of this line of thinking is its sheer audacity. It doesn't try to explain why the quantum vacuum energy is so large. It accepts that calculation and then builds a firewall between that energy and the force of gravity. This transforms the cosmological constant problem from a question of why is the number so small to what is the mechanism that protects us from its true size. It suggests that the stability of our cosmos, the very possibility of our existence, relies on a profound and hidden symmetry or a global property of the universe that ensures the most violent energies of the quantum world are kept in a gravitational cage, allowing the serene, large-scale universe we observe to emerge. While these ideas are highly theoretical and far from proven, they represent a crucial shift in the battle against the greatest numerical puzzle in cosmology, moving beyond mere adjustment of constants and toward a deeper understanding of how gravity and the quantum world ultimately negotiate their uneasy truce. While our journey through the cosmos has taken us from the holographic principle to the possibility of a simulated reality, we now venture into a theory that reimagines the very stage upon which the universe plays out. Welcome to the world of the black string and higher dimensional collapse, a concept that pulls the curtain back to reveal a cosmic drama unfolding in more dimensions than we can perceive. The central idea here is as thrilling as it is complex. What we experience as the accelerating expansion of our three-dimensional universe might not be a native phenomenon at all. Instead, it could be a shadow, a mere projection of a catastrophic event occurring in the unseen, compact dimensions of space predicted by string theory. To grasp this, we need to first visualize one of string theory's most fascinating hypothetical objects, the black string. We are familiar with a black hole, a point of immense density that warps the three dimensions of space and time into a singularity. A black string is its higher dimensional cousin. Imagine taking a black hole and stretching it out into a long, thin, one-dimensional filament, like a cosmic strand of spaghetti, but existing in a universe with more than three spatial dimensions. This object possesses an event horizon just like a black hole, but it extends infinitely through one of the extra compact dimensions. Now, according to certain string theory models, our entire three-dimensional universe, our brain, could be embedded within or attached to such a black string. Our brain is like a vast flat sheet, and this black string is like a long, dense thread running through the higher dimensional bulk parallel to our world. The gravitational field of this black string would permeate our brain, influencing the physics we experience. The crucial twist in this narrative is instability. In the higher dimensional bulk, a black string is theorized to be subject to a violent instability, known as the Gregory-Laflamme instability. Over time, this infinitely long, uniform string is prone to breaking apart, pinching off into a series of separate black holes, much like a stream of water breaking up into individual droplets due to surface tension. This is not a gentle process. It is a fundamental rearrangement of the gravitational object in the higher dimensional space. So, how does this dramatic collapse in the extra dimensions translate into what we see in our own? The mathematics of general relativity, when applied to such a setup, reveals a breathtaking connection. As the black string undergoes this instability and begins to contract or fragment in the higher dimensional bulk, the projection of its gravitational field onto our three-dimensional brain does not appear as a collapse. From our limited three-dimensional perspective trapped on our membrane, this higher dimensional contraction manifests as an accelerating expansion. It's a cosmic illusion of the highest order. Think of it like watching a shadow puppet on a wall. The puppet itself might be moving its hands closer together, but the shadow cast on the wall could be growing larger and stretching outward. You are interpreting a contraction in the higher dimensional reality as an expansion in your lower dimensional view. In this model, the mysterious force we call dark energy is stripped of its ethereal nature. It is not a new form of energy inherent to the vacuum. It is the gravitational signature of a decaying black string in the bulk, a side effect of higher dimensional geometry and instability. The relentless push driving galaxies apart is, in truth, the distant echo of a string snapping in a dimension we cannot access. This framework provides a stunningly elegant alternative to the cosmological constant, one that is inherently rooted in the geometric fabric of string theory. It bypasses the thorny cosmological constant problem by suggesting that the vacuum energy we calculate in our three dimensions is not the primary player. The real action is happening next door in the compactified dimensions. The value of the observed acceleration is then not a random, finely tuned number, but a consequence of the specific properties of the black string, its tension, its rate of collapse, and the geometry of the extra dimensions. This idea naturally extends to other higher dimensional objects, like brains of different dimensions. Perhaps our universe is not attached to a black string, but is itself a brain that is dynamically evolving in the bulk. Its expansion could be tied to its own motion or interaction with other brains. In some scenarios, the observed acceleration could be a precursor to a future collision or a phase transition in the higher dimensional space, an event that would completely reshape our cosmos from the outside in. The challenge, as with many string theory-inspired concepts, is empirical evidence. How could we ever test for the existence of a black string in a hidden dimension? The answer may lie in the subtle details of the universe's expansion history. A model driven by a decaying black string would predict a very specific evolution for the dark energy equation of state, different from a simple, constant cosmological constant or a slowly rolling quintessence field. Future missions like the ESA's Euclid Telescope or NASA's Nancy Grace Roman Space Telescope are designed to measure this expansion history with unprecedented precision, hunting for any deviation from the standard model. If they were to find a signature that matches the predicted decay of a higher dimensional object, it would be one of the most profound discoveries in the history of science. Furthermore, such a geometric origin for dark energy could leave an imprint on the cosmic gravitational wave background. The violent fragmentation of a black string would unleash a storm of gravitational radiation in the higher dimensional bulk. While we couldn't detect these waves directly, their energy could subtly influence the evolution of our brain, potentially leaving a faint statistical signature in the large-scale structure of the universe or in the spectrum of primordial gravitational waves that might one day be detected. The theory of the black string and higher dimensional collapse offers a radical and majestic vision. It tells us that to understand the fate of our own universe, we may need to look beyond its apparent boundaries, into the hidden folds of reality where strings dance and brains collide, and where a cosmic collapse in an unseen dimension is the true engine of our expanding sky. Now, if the idea of a self-creating cosmos or a universe projected from a black hole's interior has stretched your conception of reality, prepare for a theory that challenges one of the most fundamental principles governing our existence, the relentless march toward equilibrium. This brings us to the truly mind-bending world of time crystals and non-equilibrium thermodynamics, concepts that suggest the cosmos itself might be a kind of perpetual motion machine, forever resisting the quiet death of maximum entropy. At the heart of this radical idea is a new state of matter, first proposed by Nobel laureate Frank Wilczek in 2012, known as a time crystal. To understand what this is, forget everything you know about crystals for a moment. An ordinary crystal, like a diamond, has atoms arranged in a repeating pattern in space. Its structure is periodic and breaks the symmetry of space, meaning it looks the same only if you shift your perspective by a specific distance. A time crystal does something analogous but for time. Its internal structure undergoes a continuous, repeating cycle of motion, a persistent oscillation, even when it's in its lowest possible energy state, its ground state. Think of a perfectly frictionless clock that continues to tick forever without any wind-up, any battery, or any energy input whatsoever. It's not creating energy from nothing, which would violate the conservation laws. Instead, it's a system that has found a way to be in perpetual motion without ever settling down into a boring, static equilibrium. This seemingly impossible behavior was initially met with skepticism, but in 2017, two separate teams of researchers successfully created microscopic time crystals in the lab, using complex systems of trapped ions or dense clouds of atoms. These weren't perpetual motion machines in the classical sense, but they were quantum systems that exhibited a stable, periodic rhythm in time, spontaneously breaking time translation symmetry. Their existence proves that under the right conditions, matter can organize itself not just in space, but in time, achieving a form of dynamic order that defies our traditional understanding of rest. So, what happens when we take this bizarre quantum phenomenon and scale it up to the absolute limit? Could the universe itself host time crystals, or perhaps even be one? This is where the concept connects to the grand dynamics of cosmic expansion. Our standard view of the universe's fate, the heat death, is the ultimate equilibrium. It's a state where everything is the same temperature, no energy can be extracted to do work, and all processes grind to a halt, a cosmic standstill. But what if the universe is fundamentally incapable of reaching that state? What if it's inherently a non-equilibrium system, constantly driven by some internal engine that prevents it from ever settling down? This is where cosmological time crystals enter the picture. Some theoretical physicists have speculated that certain fields that permeate all of space, like the Higgs field or even the enigmatic inflaton field responsible for the Big Bang's inflation, could exist in a time crystalline phase. Imagine the fabric of the vacuum not as a still pond, but as a cosmic jello that is constantly, imperceptibly jiggling in a regular, repeating pattern across all of space and time. This persistent oscillation wouldn't consume net energy, but it could have profound gravitational consequences. The rhythmic expansion and contraction of this field's potential energy could impart a tiny, repeating push and pull on the fabric of spacetime itself. While the net effect over immense timescales might average out to the gentle acceleration we attribute to dark energy, the underlying mechanism would be radically different, not a static cosmological constant, but a dynamic, ticking heart at the core of reality. This perspective completely reframes the arrow of time. We've always thought of the increase of entropy, the progression from order to disorder, as the reason time has a direction. But in a universe with cosmic time crystals, the arrow of time could be an emergent property of this perpetual, non-equilibrium cycling. The expansion we see wouldn't be a simple coasting from an initial explosion. It would be part of a grand, unending cycle of phase transitions and symmetry-breaking events, a cosmic dance that never stops. The universe wouldn't be running down. It would be forever winding and unwinding in a complex temporal pattern we are only beginning to glimpse. This idea finds a powerful ally in the study of non-equilibrium thermodynamics, which deals with systems that are kept far from equilibrium by a constant flow of energy. A whirlpool in a river is a perfect example. It maintains its beautiful, ordered structure not in spite of the flowing water, but because of it. The moment the flow stops, the whirlpool vanishes into equilibrium. Now consider the universe. What if the primordial flow of energy from the Big Bang has set up the cosmos as a vast, non-equilibrium system? The ongoing expansion itself could be the driving force that prevents total equilibrium, creating conditions where large-scale time crystalline order can emerge and persist. In this view, dark energy is not a mysterious substance, but a signature of the universe's inherent restlessness, a thermodynamic phenomenon arising from its perpetual state of being out of balance. The acceleration isn't a push toward a cold, dark end, but evidence of an ongoing cosmic process, a phase of its eternal time crystalline evolution. While these ideas are at the very frontier of theoretical physics and remain highly speculative, they represent a profound shift in how we think about cosmic destiny. They suggest that the universe is not a one-way trip to quiet stagnation, but a dynamic, ever-changing entity with a hidden, rhythmic pulse, forever ticking against the silent pull of entropy. Now, let's turn our attention to one of the most abundant yet elusive particles in the cosmos, a ghostly messenger from the Big Bang that might hold a subtle but vital key to the universe's expansion. This is the world of neutrino-driven cosmology. Billions of these nearly massless, chargeless particles are streaming through your body every second, almost entirely without interaction, a silent echo of the universe's fiery birth. For decades, we thought neutrinos were completely massless, mere spectators in the cosmic drama. But groundbreaking discoveries have revealed that they do possess a tiny, almost imperceptible mass, and this slight heaviness transforms them from bit players into potential architects of our cosmic fate. Just after the Big Bang, the universe was so hot and dense that neutrinos were produced in staggering numbers, scattering off electrons and protons in a thick, opaque plasma. As the cosmos expanded and cooled, roughly 1 second after the beginning, these neutrinos decoupled from matter, flying freely through space and forming a cosmic background sea, much like the cosmic microwave background of light, but for neutrinos. This relic neutrino background is still all around us, an invisible fog with potentially billions of these particles in every cubic meter. Now, if neutrinos have even a minuscule mass, as we now know they do, their collective gravitational influence adds up. Across the entire observable universe, this sea of relic neutrinos contributes to the overall energy density, subtly shaping the rate of cosmic expansion. In the early universe, when they were moving at almost the speed of light, they behaved like radiation, their energy diluted by the stretching of space. But as the expansion slowed them down, there came a point when their energy became dominated by their mass rather than their motion, causing them to transition into behaving more like matter. This shift from a radiation-like component to a matter-like component in the cosmic energy budget leaves a subtle imprint on the formation of the largest structures in the universe, an imprint that might be detectable in the intricate web of galaxy clusters. But the story becomes even more intriguing when we consider the strange and wondrous properties of neutrinos themselves. These particles are quantum chameleons, constantly oscillating between their 3 different types or flavors: electron, muon, and tau neutrinos as they travel. This oscillation is only possible because the mass states that propagate through space are different from the flavor states we detect. The phenomenon implies that neutrinos have mass, but the exact mechanism behind that mass remains one of the great unsolved puzzles in particle physics. Are their masses generated by the standard Higgs mechanism, like other particles, or is there something more exotic at play, like a seesaw mechanism involving incredibly heavy, sterile neutrinos that we have yet to discover? This question is not just academic, it opens the door to a realm of speculative theories where neutrinos could be the bridge to the hidden dark sector of the universe. Imagine a scenario where neutrinos don't just oscillate among themselves, but also interact feebly with the particles that make up dark matter. This interaction could allow energy to be transferred between the visible and dark sectors of the cosmos, effectively changing the expansion history of the universe in a detectable way. In one compelling model, this interaction could cause a delayed onset of cosmic acceleration. For billions of years, the universe would expand as expected, with gravity slowing it down. Then, as neutrinos reach a specific low-energy threshold due to the cosmic expansion, their enhanced interaction with dark energy or the dark sector could trigger a phase transition, suddenly amplifying the repulsive force and kicking the acceleration into gear. This would provide a natural explanation for why dark energy became dominant only relatively recently in cosmic history, a puzzle for the simple cosmological constant model. Another radical possibility involves neutrino decay. What if the heavier mass states of neutrinos are not perfectly stable? Over cosmological timescales, they could decay into lighter neutrinos and other, perhaps invisible, particles. The energy released in this vast, slow-motion decay process happening across the cosmos could inject a new form of pressure or energy into the universe, influencing the expansion rate in a way that mimics dark energy. We would be witnessing not a static vacuum energy, but a dynamic process fueled by the gradual transformation of the neutrino background itself. The hunt for evidence of these ideas is driving some of the most sensitive experiments in the world. Huge underground detectors like Super Kamiok and in Japan, and the upcoming Deep Underground Neutrino experiment in the United States are meticulously studying neutrino oscillations and searching for signs of decay or interactions with dark matter. Meanwhile, cosmologists are scouring the most precise maps of the cosmic microwave background and the large-scale distribution of galaxies, looking for the unique signature that a neutrino-influenced dark energy would leave behind. It's a testament to the profound interconnectedness of the cosmos that the tiniest shred of mass, carried by the most ghostly of particles, could potentially hold the answer to the largest question of all, the ultimate fate of our expanding universe. Think of a river flowing smoothly over a waterfall. From a distance, its surface looks like a continuous flowing sheet. But we know this is an illusion. That smooth surface is actually made of countless individual water molecules. The river's behavior emerges from the collective dance of all those tiny parts. Now apply that same logic to the cosmos itself. What if the smooth, continuous fabric of spacetime described by Einstein, the stage on which planets and galaxies move, isn't fundamental? What if it too is an emergent property, a large-scale illusion arising from something far more basic and chaotic? This is the radical premise of the emergent spacetime paradigm, a theory that draws a powerful analogy from the world of condensed matter physics. In this view, spacetime isn't the starting point of reality. It's the end product condensing out of a more primitive, underlying system, much like the flow of a liquid emerges from the frenetic motion of its atoms. This perspective completely inverts our traditional understanding. For over a century, we've treated spacetime as the immutable canvas, but if it's emergent, then concepts like distance, duration, and even the expansion of the universe are not primary features. They are collective behaviors, the way a crowd moves, not the way a single person walks. This opens up a breathtaking new way to model the cosmos, using systems we can actually study in the lab. Consider a Bose-Einstein condensate, a state of matter where a cloud of atoms is cooled to near absolute zero. At this point, the atoms lose their individual identities and merge into a single, coherent quantum wave, a superfluid that can flow without any friction. Now, imagine introducing a tiny disturbance into this superfluid, like a sound wave. The mathematics describing how that sound wave moves through the condensate can be exactly the same as the mathematics describing how light moves through a curved spacetime in general relativity. The condensate itself acts as an analog for the vacuum of space, and the sound wave plays the role of light. Even more astonishingly, by carefully manipulating the condensate, physicists can create an effective event horizon for these sound waves, an analog of a black hole from which sound cannot escape. This entire field of research is known as analog gravity, and it provides a revolutionary sandbox for testing ideas about quantum gravity and cosmic expansion. We can't recreate the Big Bang in a lab, but we can create a superfluid that mathematically mimics its expanding geometry. If we set up a Bose-Einstein condensate to expand in a specific way, the behavior of excitations within it can tell us something profound about how quantum fields behave in our own expanding universe. The ripples and vibrations in the condensate are analogous to the primordial quantum fluctuations that were stretched during cosmic inflation to become the seeds for all the galaxies we see today. By watching these analog universes evolve, we can gain insights into how our own might have unfolded. This approach suggests a stunning possibility for what drives cosmic expansion. In the emergent spacetime picture, the accelerating expansion we attribute to dark energy might not be caused by a mysterious substance. Instead, it could be a thermodynamic phenomenon, a natural relaxation of the underlying system as it evolves toward a state of equilibrium, much like a gas expanding to fill a vacuum. The expansion is not a force pushing things apart, but the natural, large-scale consequence of the microscopic components rearranging themselves. This elegantly sidesteps the infamous cosmological constant problem, because the vacuum energy of quantum fields might not directly gravitate in this picture. It's just part of the internal energy of the underlying system, whose collective behavior manifests as the gentle, repulsive push we measure. The implications ripple out to the very beginning of time. The Big Bang singularity, that point of infinite density where our laws of physics break down, might simply be the point where our emergent description of spacetime ceases to be valid. It's not that the universe was infinitely small, but that the analogy breaks down just as the concept of a smooth water surface breaks down when you look at the scale of individual molecules. Before the emergence of classical spacetime, the universe could have been in a primordial, chaotic phase, a cosmic superfluid or a condensate of fundamental building blocks, perhaps strings or loops, that only later crystallized into the familiar dimensions of space and time. The initial rapid expansion of inflation could then be understood as a phase transition, similar to water freezing into ice or a superfluid becoming turbulent, where the orderly structure of spacetime itself rapidly nucleated and grew from that formless quantum background. Exploring the universe through this lens transforms it from a container of things into a dynamic, collective phenomenon. It suggests that the force of gravity itself may not be fundamental, but rather, it's the thermodynamic force that arises from the universe's tendency to maximize its entropy, a concept we touched on with emergent gravity. The majestic expansion of the cosmos, carrying galaxies away from one another, could be the grandest emergent behavior of all, the final, slow-moving wave on a deep and hidden quantum sea. But to truly grasp the most violent potential fate for our cosmos, we have to push the idea of dark energy to its absolute limit, into a domain so extreme it makes the cosmological constant seem almost gentle. This brings us to the terrifying and fascinating theory of phantom energy and the ultimate cosmic doomsday known as the Big Rip. We've discussed how quintessence can be a dynamic field, but phantom energy is a specific, nightmarish flavor of it. For any form of energy in cosmology, scientists describe its properties with a number called the equation of state parameter, denoted by W. It's the ratio of the pressure the energy exerts to its energy density. For normal matter, W is 0. For radiation, W is 1/3. For the simple cosmological constant model of dark energy, W is exactly -1, but for phantom energy, W is less than -1. It is more negative than the cosmological constant. This seemingly small mathematical distinction has catastrophic consequences. A cosmological constant has a steady energy density as the universe expands. But if W is less than -1, it means the pressure is so hugely negative that it acts as a tension stronger than anything we know. And this has a bizarre effect. The density of phantom energy doesn't stay constant or decrease as the universe grows. It actually increases over time. Think of it like a strange cosmic spring that gets harder to stretch the more you pull it. As the universe expands, creating more volume, the amount of this repulsive phantom energy grows, which in turn makes the expansion accelerate even faster, which creates more space, which increases the phantom energy density even more. It's a runaway feedback loop of repulsive gravity, a vicious cycle with no natural break. Now, let's follow this logic to its grisly conclusion, the Big Rip scenario. In a universe dominated by such a phantom field, the acceleration doesn't just continue forever. It intensifies exponentially, becoming infinitely powerful in a finite amount of time. The first casualties in this cosmic apocalypse would be the largest structures held together by the weakest bonds. About 60 million years before the end, the phantom energy's repulsive force would overcome the gravitational glue holding galaxy clusters together. These vast cities of stars would be flung apart into the accelerating darkness. Then, as we approach the final months, the tension would become so immense that it would overwhelm the gravity binding individual galaxies. The Milky Way, Andromeda, and all their stars would be torn asunder, each star becoming an isolated island rushing away from all others. In the last minutes, the horror would come home. The phantom force would exceed the gravitational bond holding our solar system together. Planets would be ripped from their orbits around the sun, sent careening into the void. Then it would target the stars and planets themselves. About half an hour before the final moment, the expansion force would surpass the chemical bonds holding our Earth together. The very planet would explode, its fragments violently pulled apart. In the last terrifying instance, the forces that hold atoms together, the electromagnetic bonds between nuclei and electrons, would be overcome. Every molecule, every atom in the universe would be shredded into a diffuse cloud of fundamental particles. And finally, in the last inconceivable fraction of a second, the fabric of space-time itself might be torn apart, dissolving the very stage upon which the cosmic drama has played out. The universe would end not with a crunch or a fade, but with a fundamental and violent disintegration of all structure. Is such a thing theoretically possible? The mathematics of general relativity certainly allows for it. An equation of state with W less than -1 is not forbidden by the theory. However, it raises profound questions about the physical nature of such a field. Phantom energy violates what is known as the null energy condition, a principle that many physicists believe is a fundamental requirement for any reasonable form of matter and energy. It implies negative kinetic energy, which can lead to instabilities and causality paradoxes, like the potential for messages to be sent backward in time. So while the equations permit it, the physics behind it is deeply strange and considered by many to be unphysical. The ultimate arbiter, as always, is observation. Astronomers have been working tirelessly to measure the value of W for our dark energy. Does it match the cosmological constant's -1, or does it stray into the phantom zone? The current data from the cosmic microwave background, distant supernova, and large-scale galaxy surveys all point to a value very close to -1. In fact, the best measurements to date suggest W is approximately -0.95, with error bars that comfortably include -1 and only slightly dip into the phantom regime. So far, the universe shows no conclusive evidence that it is hosting this most destructive of tenets. the data is consistent with a far more gentle, if still eternally lonely, fate. Yet the phantom energy and the Big Rip remain a vital part of the cosmological conversation. They represent the outer boundary of possibility, a stark reminder of how profoundly the specific character of dark energy dictates our ultimate destiny. They challenge our theories and force us to ask the most fundamental questions about what kinds of energy can truly exist in our universe and what the final act of our cosmic story will ultimately be. We've arrived at the final frontier of our journey, a theory that confronts one of the most deeply held assumptions in all of physics, an assumption that, if broken, could rewrite the rules of reality and open the door to phenomena straight out of science fiction. This is the theory of the null energy condition violation and the existence of exotic matter. To understand this, we first need to grasp what the null energy condition actually is. In Einstein's theory of general relativity, there are certain rules about what kinds of matter and energy are physically reasonable. The null energy condition, or NEC, is one of the most fundamental of these rules. In simple terms, it states that for any light-like ray of light traveling through space, the energy density it encounters must always be non-negative. It essentially forbids negative energy densities. This isn't just a mathematical nicety. It's the bedrock principle that prevents a host of cosmic catastrophes and paradoxes. It ensures that gravity is always attractive, that wormholes don't spontaneously form in your living room, and most importantly, that cause always precedes effect, preserving the logical flow of time and preventing time travel. It's the universe's way of saying that energy cannot be less than nothing. But what if, under certain extreme conditions, this rule could be bent or even broken? The implications are staggering. Let's start with the very beginning of everything. We've discussed cosmic inflation, that period of stupendous expansion that smoothed out the early universe. The driving force behind inflation was a field stuck in a high-energy state, whose repulsive gravity blew the universe apart. For this to work, the pressure of this field had to be negative and large in magnitude. In fact, for the rapid, exponential expansion of inflation to occur, the null energy condition had to be violated, at least temporarily. The inflattened field had to possess a form of energy that, from a certain perspective, acts like a negative energy density, creating the anti-gravity needed to drive the expansion. So, in a very real sense, the large-scale structure of our entire observable universe, the existence of galaxies, stars, and us, may be a direct consequence of the universe briefly breaking its own most sacred energy rule in its first fleeting moments. This violation wasn't a bug, it was a feature, a necessary ingredient for creation itself. This concept doesn't just apply to the ancient past. The mysterious dark energy driving the accelerated expansion of the universe today also pushes against the boundaries of the null energy condition. The simple cosmological constant, with its equation of state of exactly -1, sits right on the razor's edge of what is allowed. But if dark energy is something more dynamic, like the phantom energy we discussed, with an equation of state less than -1, then it represents a clear and sustained violation of the null energy condition in the present day. This is the realm of what physicists call exotic matter. This isn't just dark matter, which is mysterious but still has positive energy density. Exotic matter is something far stranger, a substance with a negative energy density. If you could hold a chunk of this stuff, it would theoretically weigh less than nothing. It would experience gravity in reverse, being repelled by, rather than attracted to, normal matter. The potential applications of such a material are the stuff of legend. The most famous is the stable wormhole, often called an Einstein-Rosen bridge. In general relativity, wormholes are theoretical shortcuts through space-time, but the ones that appear naturally in the equations are unstable. They would snap shut in an instant, far too quickly for even a photon to pass through. However, if you could line the throat of a wormhole with a shell of this exotic matter, its negative energy would generate a repulsive gravitational force that could theoretically prop the wormhole open, creating a stable tunnel connecting two distant points in space and time. Similarly, the theoretical Alcubierre warp drive, a concept for faster-than-light travel, requires a shell of exotic matter with negative energy density to contract spacetime in front of a spacecraft and expand it behind, effectively allowing the ship to ride a wave of distorted spacetime without ever locally exceeding the speed of light. And yes, the most troubling application is closed time-like curves, theoretical paths through spacetime that loop back on themselves, allowing for the possibility of time travel into the past with all the mind-bending paradoxes that entails, like the famous grandfather paradox. So, what could this exotic matter actually be? It's not something you can mine from an asteroid. The leading candidates are purely quantum in nature. The Casimir effect provides a tantalizing hint. If you take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum, they will be spontaneously pulled toward each other. Why? Because the space between the plates restricts the kinds of quantum fluctuations that can pop in and out of existence. This creates a lower energy density in the gap between the plates than in the empty space outside them. Relative to the outside, the region between the plates effectively has a negative energy density. It's a tiny, microscopic, and fleeting violation of the null energy condition sanctioned by quantum mechanics. Some theories suggest that certain dynamic fields, like some versions of the quintessence field we've discussed, could achieve a sustained, large-scale version of this effect, acting as the exotic matter needed to drive cosmic acceleration or even stabilize a wormhole. However, the universe seems to have powerful safeguards against this, allowing large-scale, classical violations of the null energy condition introduces profound instabilities. The vacuum could become unstable, decaying into a cascade of particles or even causing spacetime itself to tear. The most concerning implications are causal. If you can violate the NEC, you can, in principle, create configurations that allow for time travel, shattering our understanding of cause and effect. The fact that we don't see time travelers from the future might be the strongest empirical evidence that sustained, macroscopic violations of the null energy condition are forbidden by a deeper law of physics we have yet to discover. This creates a thrilling tension at the heart of modern physics. Our best theory of the cosmos, including its beginning and its present acceleration, seems to require a delicate dance with this forbidden energy. Yet, actually harvesting and controlling it seems to unleash chaos. It's as if the universe used a one-time only emergency override to get itself started, but has since locked away the keys to prevent us from tampering with the fundamental pillars of reality. Exploring this boundary is where our current understanding ends, pointing toward the need for a final theory that can tell us why the rules are what they are, and whether they can ever, even for a moment, be broken. We have ventured across an astonishing landscape of cosmic possibilities, from the dark energy accelerating our universe's growth to the holographic projection of our reality, from eternal inflation spawning infinite bubble universes to the rhythmic pulse of a cosmos that collapses and rebounds in an endless cycle. We've questioned the constancy of light and gravity, explored the idea that our universe might be the interior of a black hole, and even dared to consider that all we see could be an elaborate simulation or a time crystal forever resisting equilibrium. This journey through 30 distinct visions reveals a profound truth. The question of our cosmic fate is not a puzzle with a single solution, but a vibrant, open field of inquiry where the most daring ideas in physics are born and tested. The fact that brilliant minds can construct such wildly different, yet mathematically coherent, models for the same observable reality is a testament to the boundless creativity of the human spirit when faced with the ultimate mystery. It shows that science at its frontier is not just a collection of facts, but a dynamic, living process of imagination and rigorous debate. a collective striving to understand our place in this vast, expanding reality. While the definitive answer to where the universe is headed remains hidden from us for now, the value lies in the search itself, a search that pushes the very boundaries of logic, matter, and space-time. Each theory, whether it ultimately proves correct or not, adds a new color to our map of the possible, deepening our appreciation for the complexity and wonder of the cosmos we call home. So, as we bring this exploration to a close, we turn the question over to you. Which of these cosmic destinies captures your imagination the most? Does the serene, eternal expansion of a dark energy-dominated future feel right? Or does the dramatic, cyclical rebirth of a bouncing universe resonate more deeply with you? Perhaps the idea of a holographic universe or a vast multiverse where every possibility is real is the vision that sets your mind alight. We would love to hear your thoughts and continue the conversation in the comments below. If you enjoyed this journey to the edge of cosmology, be sure to subscribe and hit the notification bell so you don't miss our next adventure into the deepest mysteries of space, time, and reality. Thank you for exploring the